Good evening, everyone. Welcome to BYJU'S Exam Prep. So, welcome everyone for this session. So, this is a marathon session. As you all know that we are running marathon series. So, एक बार फटाफट यार कमेंट सेक्शन में कमेंट कर दो कि you all are live and आपको ऑडियो एंड वीडियो क्लियर है. ठीक है. Once the audio video will be clear, so we will be starting our marathon series. That is the revision marathon. Okay, that is the revision marathon, and we will be going through all the concept of communication in one shot. Okay, in one shot, we are going to cover the entire syllabus of communication system. So, just quickly tell me once about the upcoming, voice and video, everything is clear or not. Yes, good evening, Banu. Good evening, Kunal. Yes, good evening. Okay. So guys, today we are going to start the communication system, and we are going to start from the basic, that is your modulation, and after that we are going to discuss about your amplitude modulation, angle modulation, random variable, random process, all these things we are going to discuss. And for every concept we are going through the theoretical part, not the questions. So we are not going to revise through the questions, and we are going to learn from the theoretical point of view only. Questions you have to practice, and we will take more question session also, like concept through questions, that will be in the next week. So today we are having the complete theoretical series. And before starting this session, I would like to introduce myself. So this is Saket Verma. I am having more than 13 years of experience, and this is my Telegram group. You can join this Telegram group for the upcoming updates of all the coming sessions. And these are all about myself. So I have done MTech from IIT Guwahati, cracked a different PSU exam as well. And my area of expertise are communication system and electromagnetic theory, advanced communication system, signal system, ICT also for EAC. So you all know that we have already started our revision series, and guys, whenever there will be a break in this session, because this is a marathon session, so there may be a multiple breaks around 10 to 15 minutes, or maybe around a dinner break. So during the break, you will be getting a QR code, and in that QR code, you can appear in the quiz of this session. So for this particular session and for every revision session, we have created one quiz. So you can go through that QR code. I will share the QR code link during the break, and just scan that QR code, and you will directly go to the link of the quiz. So you can directly appear on the quiz of the communication system and the rest of the subjects which you have completed during the break. Okay. So guys, we will start from the modulation. So what is the modulation? If we start modulation, then it is nothing but the process in which the low frequency signal is translated into the high frequency signal. So when we perform the modulation, we actually convert our low frequency signal into high frequency signal. So to convert this low frequency signal into high frequency signal, we multiply with the high frequency signal, and that is known as the frequency translation. So modulation can be defined in the multiple ways. First is the frequency translation. Whenever you multiply, you will get the translation of the frequency. So two signals are multiplied, and whenever we multiply the two signals having some frequency, then it will be generating the summation signal and the difference between the signals. Now the second definition says that we will be having the two signals. So one signal characteristics will be changed according to the characteristics of another signal. Suppose we have one signal M1 and another signal M2. So we will keep one parameter constant, and we will change the parameter of those constant signal. That means suppose I have taken the M2 as a cosine signal, then that characteristics of those cosine signal will be changed according to my first signal. So the first signal can be anything, but the second signal will be fixed. So according to the characteristics of the first waveform, the characteristics of the second waveform will be changed. That is called another definition of your modulation. So there are two ways, and whenever we perform the modulation, our low frequency signal converts into the high frequency, and also we say that low pass signal converts into band pass signal. Low pass signal converts into band pass signal. So that happens when we perform the modulation. So these are the three things that you should know about the modulation, because sometimes they can ask you that which one of the following is a band pass signal. So the signal which is modulated is called as a band pass signal. The signal which is not modulated is called a low pass signal most of the time. There may be some cases when the low pass signal, your information signal may also be a band pass signal, but that is very rare and that will be mentioned to you. But by default, all the message signals are taken as the low frequency signal and the low pass signal. So that is about your modulation. Now, how do we perform the modulation? So to perform the modulation, we consider low frequency signal, because using the modulation, we convert our analog signal in the low frequency to the high frequency. So let's choose any one low frequency signal, low frequency or low pass, which is having the frequency 5 kilohertz. So we have a triangular waveform which is varying from -FM to FM in kilohertz. Now this waveform has to be converted into the high frequency. So to convert it into the high frequency, we will multiply it with the high frequency signal, and to multiply that, we will take the balance modulator. The balance modulator is a circuit which multiplies the input signals. So in the balance modulator, the input signals are MT and cos 2 pi FCT. So these two signals will be multiplied to generate our output signal. And this FC, which is a carrier signal, we are calling this as a carrier signal because it is going to carry your information for a longer distance. So this FC is taken as 1 megahertz. So you can say that we are taking this as 1000 kilohertz. Yes, digital communication will also be covered today only. Hello Manasvi, good evening. So this is the 1000 kilohertz, and this is the message signal, which is mixer is a balanced modulator circuit. Mixer, you can call it as a balanced modulator circuit, but the name mixer given is because the purpose of the mixer is to generate the summation and the difference signal. And in the modulator block, we mostly say that we are performing the modulation. That means we are converting the low frequency signal into high frequency. So purpose of saying modulation means there will be a conversion from low frequency to high frequency. But whenever we have a mixer will always perform the addition and the subtraction of the frequency. And in the balanced modulator, there is a no low pass filter. Okay, and in the mixer circuit is followed by low pass filter. Okay, that inside the mixer itself, we will have a low pass filter. So when you multiply these two signals, you will be getting F1 plus F2 and F1 minus F2. So according to the requirement, you can take which signal you want to transmit, whether you want F1 minus F2 or you want F1 plus F2. So if you want F1 minus F2, then you will use low pass filter. But in balanced modulator, we will definitely get F1 plus F2 and F1 minus F2. We don't reject any frequency. So the difference between the mixer and the balanced modulator is the only in terms of frequency selection. In mixer, we choose appropriate frequency, but in balanced modulator, we get both the frequency. Okay. Yes, Manasvi, I am good. How about your GRE? How was it? You were preparing for that, and you were not coming into some sessions, and you said that you are preparing for the GRE. So how was your GRE paper? Okay. So here we will get F1 plus F2 and F1 minus F2. So what will be our output? So here the output YT would be your MT into cos 2 pi FCT Okay, so this will be the output, and if we take suppose the Fourier transform of this, so it is m of f minus fc plus m of f plus fc and whole divided by 2. So in this way, we say that our original message spectrum will be shifted to the carrier frequency, and the carrier frequency is 1000. So your original spectrum, this original spectrum will be shifted to 1000, which is at 5. 5 and minus 5, now it will be shifted to 1000. Here you can see, now it is shifted to 1000, and it is 1000 plus 5, 1000 minus 5, amplitude is half. So now because this signal is centered at frequency other than 0, centered at frequency other than 0, and especially at high frequency, the signal is centered at frequency other than 0, and if we say that for which frequency, so it is 1000 kilohertz, so which is a high frequency, so it is called a band pass signal. So the signal which are centered at some high frequency, most of the time we take high frequency, but it may be some other frequency also. It is not necessary that very high frequency. It may be some 10-20 kilohertz also, that will also be considered as a band pass signal if it is centered that other than 0. Any signal which is centered about 0 is called low pass, and the signal which is not centered about 0 is called high frequency signal and the band pass signal. Now, what is the need of modulation? The modulation reduces the height of antenna. This is the main advantage of getting modulation, because why we need this modulation? Because suppose we want to transmit a 3 kilohertz signal. Okay, suppose we want to transmit a 3 kilohertz signal using the Hertzian dipole antenna or half wave dipole antenna. Let us say the height of the antenna is lambda by 2, because we are considering the half wave dipole antenna. So that would be better. That half wave dipole antenna if we are using, then the length of the height of the antenna will be lambda by 2, and lambda is the wavelength. Wavelength is c upon f. C is the velocity of light, so c 3 into 10 to the power 8 divided by frequency. So which frequency we want to transmit? 3 kilohertz. So we are getting the wavelength 100, and the length of the antenna is 50 kilometers. So 50 kilometer length of antenna is not practically possible. So for that, what we will do? We will increase the frequency, because by increasing the frequency, the wavelength can be reduced, and if you reduce the wavelength, then the length of the antenna will also be reduced. So because we have translated our frequency to some high frequency, let us say 3 megahertz, by the help of modulation, here you have understood that this 3 kilohertz signal, 5 kilohertz signal, this 5 kilohertz signal is translated to 1000. Similarly, this 3 kilohertz signal is translated into 3 megahertz signal using the same balance modulator. The balance modulator which is having the 3 kilohertz and 3 megahertz. So now when you perform the modulation, you will get 3000 plus 3 and 3000 minus 3. So we will say that the output will be centered at 3000. So if we say that the output is centered at 3000, so by choosing that frequency 3000 kilohertz or 3 megahertz, we will get the lambda is equal to 100 meter, and when we calculate the height of antenna, we will get 50 kilometer, which is we can still think of realizing the 50 meter antenna instead of the creating 50 kilometer antenna. So generating the 50 designing the 50 kilometer length of antenna is little bit difficult, and what we should say, it is more difficult, and it is in fact practically unrealizable, and here the 50 meter antenna is still feasible. The second need of modulation is the modulation increases the range of communication. So because the radiated power is directly proportional to the square of frequency, so as you increase the frequency, the radiated power also increases. for any linear antenna, we can say that the radiated power is directly proportional to square of frequency. So by increasing the frequency, you can increase the radiated power. So this type of question can be framed in the EMFT also, that how much is the radiated power when the frequency is doubled, when the suppose you are transmitting the 10 kilowatt of power और आपसे पूछा जाए कि फ्रीक्वेंसी को हमने 4 टाइम्स कर दिया है, तो जो रेडिएटेड पावर है वो कितना हो जाएगा, that will be 16 times. So 16 times of the previous power that you were transmitted. Okay, suppose हमारे पास दे दिया 1 megahertz. Okay, 1 megahertz with the frequency 1 megahertz, the radiated power is 4 kilowatt. Then if suppose this is 10 megahertz, so the frequency is doubled 10 times, so the power will be 10 square times of 4 kilowatt. So that is obviously not possible. 400 kilowatt antenna is very huge by transmitting through the antenna, but still just an example I am saying. Okay, so in this way you can say that the frequency is related to the radiated power. This can question be coming from the EMFT also. Okay, and modulation also overcomes the hardware limitation. So when you perform the modulation, your hardware requirement will also get reduced, and it will become easier to design the hardware, because the fractional bandwidth, for practical hardware implementation, the fractional bandwidth should be 1 to 10%. So it should be 1 to 10%. And what do you mean by the fractional bandwidth? So it is nothing but the bandwidth upon the center frequency. So bandwidth upon center frequency, how do you calculate bandwidth upon center frequency? So this is our message signal spectrum. Now the bandwidth we have calculated once we modulated it, and before modulation, what is this? So let's see here, the before modulation, when you will see, this is the bandwidth is 5 and the center frequency is 0, so fractional bandwidth is huge. Let us say this is modulated using the 10 kilohertz. So we are modulating it using the 10 kilohertz. So here we have. So if you modulate it using the 10 kilohertz only, we will modulate it using 10 kilohertz and we will modulate it using 100 kilohertz. Then you will understand what is the meaning of fractional bandwidth. So if you are modulating it using 10 kilohertz, so if it is 10 kilohertz, so it is 15 and it is 5, because our message signal frequency was 5 kilohertz and the carrier frequency we have taken as 10 kilohertz. So it is 10 plus 5 and 10 minus 5. So it is minus 10, minus 5 and minus 50. So here if you will calculate the fractional bandwidth, okay, so fractional bandwidth is your bandwidth divided by center frequency. So bandwidth is, the bandwidth here is 10. So 10 divided by 10 into 100. So percentage fractional bandwidth we are calculating. So it is 100%. So in this case, it is coming as 100%. Now, when I take the center frequency or the carrier frequency, FM is equal to 5 kilohertz and it is suppose 1000 kilohertz. Now I am taking the center frequency 1000 kilohertz. So here if I shift it to the 1000, then it is 1000 and it is 1005. This is 995 and it is minus 1000, minus 995 and minus 1005. So what will be our fractional bandwidth? Percentage fractional bandwidth. So percentage fractional bandwidth is center frequency. What is the center frequency? 1000. The bandwidth is how much? That is 10 into 100. Sorry, just reverse now. The bandwidth is 10 and the center frequency is 1000. So here it is 1%. So it is coming as 1%. So by using the modulation with very high frequency, so modulation, after modulation with the high frequency, you can see that the fractional bandwidth is reduced. Fractional bandwidth is reduced by almost 100%. Okay, by factor 10. So in this case, you will see that we are going to have the fractional bandwidth in between 1 to 10%. So if it is 1 to 10%, then hardware implementation is easy. So here in this case, even if we are modulating, but if the modulation is done in low frequency, then it is difficult for hardware implementation. So that is why after modulation with high frequency, it can be easily acquired. Yes, fractional bandwidth is somewhat related to narrow band. Okay, fractional bandwidth is, that means you are creating the narrow band signal. Narrow band signal will have the less bandwidth and the high center frequency. So that is, you can definitely call it as a narrow band signal. Okay, yes, I will be using the dark signal, but in between somewhere, suppose there is some extra slide required, so that may be a white, but yes, I can keep that also black. So don't worry, I will take care of that. Okay, I will be using the black background, no issue. Now you need to solve this question, and we have two signals x1 and x2, and it is passed through some filter which is defined by the rectangular function, and then these signals are multiplied. You have to calculate the bandwidth of such type of signal. Okay, so can you answer this question? शरीफ लड़के CGPA आपका 6 से ऊपर आप कर लो, 6.5 तक कर सकते हो तो अच्छा है, 6 से ऊपर भी कर लोगे तो कोई ज़्यादा दिक्कत नहीं है, बट 6.5 तक कर लो तो परसेंटेज में भी वो नियर अबाउट 60 हो जाता है। तो आप ट्राई करो कि 6.5 तक पहुंचा सको अगर पॉसिबल है तो। कुणाल आप बोल रहे हो बैंडविड्थ 6 आ रहा है, सो लेट अस सी कि क्या बैंडविड्थ आएगा। तो देखो एक रेक्टेंगुलर फंक्शन है, वी विल हैव रेक्टेंगुलर फंक्शन of 10 to the power 4t. So because this is the filter in the frequency domain, so we have to calculate the rectangular 10 to the power 4t. अच्छा CGPA, ओके ठीक है, हाँ CGPA एटलीस्ट 6 तो आपको चाहिए, 6.5 तक खींच लोगे तो बहुत अच्छी बात है। रेक्टेंगुलर फंक्शन है, ठीक है, रेक्टेंगुलर फंक्शन है, सो इसका फोरियर ट्रांसफॉर्म कितना आना चाहिए? रेक्टेंगुलर फंक्शन है, इसका फोरियर ट्रांसफॉर्म आपको मिलेगा सिंक, ठीक है। ठीक है, तो ये है हमारे पास रेक्टेंगुलर 10 टू द पावर 4t, ठीक है, 10 टू द पावर 4t है। अब इसका क्या मतलब हुआ कि विड्थ इसका 10 टू द पावर -4 है ना, t अपॉन कैपिटल T होता है, तो नीचे जाएगा तो ये 10 टू पावर -4 हो जाएगा, तो विड्थ इसका 10 टू पावर -4 है, सो इट मींस इट इज 0.5 इंटू 10 टू पावर -4 एंड 0 एंड -0.5 इंटू 10 टू पावर -4। तो इस तरीके से वी कैन से दैट द विड्थ इज 10 टू द पावर -4, राइट। तो जो भी विड्थ है उसका इनवर्स जो होता है दैट इज द जीरो क्रॉसिंग पॉइंट। सो जीरो क्रॉसिंग पॉइंट में कोई डाउट होगा तो बता देना, जीरो क्रॉसिंग पॉइंट में अगर आपको डाउट है तो आप बता देना, क्योंकि जीरो क्रॉसिंग पॉइंट मेरे हिसाब से 10 आना चाहिए अगर मैं किलो हर्ट्ज में बात करूं तो। and so on. Okay, so if you have any doubt, so just calculate, tell me if you have any doubt in this waveform, then I will explain that how this waveform is coming. Okay, so now this signal which we have got is passed through the high pass, low pass filter, and the low pass filter in the frequency domain, it is given that, ठीक है, यहाँ पे हमारे पास जो पहला लो पास फिल्टर है, this H1F is given as, this is 2 into 10 to the power 4, मतलब total width 2 into 10 to the power 4 है. So the total width is 2 into 10 to the power 4. So that means it will be a 10 to the power 4 and it will be a minus 10 to the power 4 in F. Okay, so this इसको अगर मैं किलोहर्ट्ज में लिखूं तो this is nothing but 10 kilohertz and minus 10 kilohertz. So this signal, this sync function is passed through the first filter. Okay, this sync function is passed through this first filter. So what we will get? So the output, the first output we will be getting, the first output we will be getting, because this is kilohertz पे मैंने लिखा है, and here you can see this is 10 to the power 4. So 10 kilohertz को मैं 10 to the power 4 लिख सकता हूँ. So I can say that we are going to get this. So ये हमारा किलोहर्ट्ज में आ गया. तो हमारा आउटपुट जो आएगा पहला, okay, so from the upper path we will get this y1t. y1t का जो फोरियर ट्रांसफॉर्म है, that would be y1f. Okay, y1t का जो फोरियर ट्रांसफॉर्म है वो y1f आएगा, and that is from minus 10 to 10. Is it clear? ये सही है, minus 10 से 10. ठीक, ये आ गया पहला. Okay, now similarly we will discuss the second part, but second part is little bit easier because this is the delta t and the impulse is having the Fourier transform 1. So the impulse will have Fourier transform 1. So this is x2 of f. So what will be the Fourier transform? That is 1. Okay, this is f. Now what is this filter? This filter is having the width 10 to the power 4. So this filter is having the width 10 to the power 4. So this filter rectangular function will have the width 10 to the power 4. So it is minus 0.5 to 10 to the power 4 plus 0.5 into 10 to the power 4. This is our second filter. Now what will be the output of this filter? So it will be ranging from minus 0.5 to 0.5 because this is all frequency, है ना, ये आपका सारे frequency में available है, but the filter will compress it, or you can say the suppress it and the band limit it in the given range. So it will be band limiting. It would be band limiting our signal from, this is our y2f. It will be band limiting our signal from again minus 0 कितना, minus 0.5 to 0.5 है. 5 लिख सकता हूँ मैं इसको किलोहर्ट्ज में. I can write it as, है ना, ये मेरे पास था minus 0.5 into 10 to the power 4, तो मैं इसको लिख रहा हूँ 5 kilohertz. Okay, now we have these two signals. Yes. Yes, इसको चेक कर लेते हैं हम लोग, है ना, मैं तो जस्ट रैंडमली लिखा हूँ. और बाकी फिर बैंडविड्थ क्या आ जाएगा, क्योंकि हमको z of t जो लिखना था, so that is y1t into y2t. Okay, y1t into y2t. So z of f is y1f convolved with y2f, and when these two signals are convolved, this y1 and y2 will convolve, then the output will be in the whatever will be the shape, but the maximum frequency will be the addition of individual frequency. So addition of individual frequency is 10 plus 5, that means 15 kilohertz. So 15 kilohertz and minus 15 kilohertz will be the output, that is final output z of f. We wanted to calculate the bandwidth of z of t. So the bandwidth of the z of t is 15. So answer is 15 kilohertz. Yes, Vikram. Now let's check whether this sync function I have calculated correctly or not, because I just put it randomly. Maybe there may be something which I have missed it. Now we have to calculate a rectangular T upon capital T is having the Fourier transform. Okay, this is having the Fourier transform AT sync FT. This is the Fourier transform. We will get now. We had 1 into rectangular of T upon 10 to the power minus 4. So when you compare this 10 to the power minus 4, because A is 1 and capital T is 10 to the power minus 4. So think of F into 10 to the power minus 4. So the zero crossing point, okay, the zero crossing we can calculate by making the sync function 0. So zero crossing point you can calculate by making this sync function 0. So this can be written as sine pi f into 10 to the power minus 4 divided by pi f into 10 to the power minus 4. Okay, so to make this 0, what we have to take, this pi f into 10 to the power minus 4 should be integer multiple of pi. So this pi and pi will get cancelled. So f is equal to n upon 10 to the power minus 4, or it will be n into 10 to the power 4, where n was integer. Okay, so when we take n equal to 1, f equal to 1 into 10 to the power 4. When we take n equal to 2, f will be 2 into 10 to the power 4. So that means it is 10 kilohertz. Okay, and this is 20 kilohertz, and so on. So the zero crossing point we will be getting 10, 20, and so on. So 10, 20, 30, and so on. I was not bothering about the magnitude because I wanted to calculate the bandwidth. So that is why in any signal I am not interested to write the amplitude, है ना? मैंने कहीं पे भी amplitude नहीं put किया है because हम लोग को सिर्फ और सिर्फ frequency domain में deal करना था, तो amplitude was not a concern for us. ठीक है भानु? Now it is clear that how I got this. Yes. ठीक है, चलो now try this question. Anyone? Guys, during this session, you can like the video also. Okay, those who have not liked the video can like the video. It has to be crossed at least more than 100. So answer you are getting is 920. Okay. So x of t is equal to mt cos 2 pi fct is given. And the message signal mt is 4 cos 1000 pi t and the carrier frequency is 1 megahertz is passed through a demodulator as shown in figure. The output of the demodulator is. Okay, so we have x of t which is mt cos 2 pi fct. fc is 1 megahertz and it is now multiplied with this. So how can we solve this question where the mt is already given? So because this mt is 4 cos 1000 pi t. Okay, so 4 cos 1000 pi t. So we are saying that we have a message signal which is 4 cos 1000 pi t. So what is the Fourier transform of this, which is m of f? M of f will be 2. Okay, that is amplitude gets half and delta f minus 500 and f plus 500. So we will have this pulse. This is our message signal right now. M of f, which is at 500 and minus 500. Remember that the amplitude is important here. Yes, as per the answer key, you are getting almost very close answer. You are getting means just close. It is expected to have the cutoff between the 65 to the 75. The range I am expecting is 65 to 75. So there is a good chance for you. You can keep hope. Okay, now the message signal is this, and now this message signal is shifted to 1000. So this message signal is shifted to 1000. This is 1000 kilohertz. Okay. This is 1 megahertz given. So let's say FC and FC plus 500 and FC minus 500. Okay, so let me write in this way only. So we are getting, this is FC and this is FC plus 500 and FC minus 500 and this is 0. This is minus FC plus 500 and minus FC minus 500. Okay, then it is shifted again. So that means it is amplitude will become half. Okay, is it clear? So the x of t, we have drawn the Fourier transform of x of t. So the amplitude get half, and because you are shifting it, so m of f minus fc, m of f plus fc divided by 2 again. So there are two Fourier transform, we will get this. Now you are shifting it again by the fc plus 40. So fc plus 40 and fc minus 40. So you will shift it by fc plus 40 and fc minus 40. Okay, so when you will shift it to the fc plus 40 and fc minus 40, so when you will shift it, so fc plus 40 you will add in the whole axis. So when you add the fc plus 40, this will be around 40. Okay, this will be, we are adding FC plus 40, FC plus 40 and FC plus 40. So how much it is? Minus 500 plus 40 will become 460 with minus sign. So minus 460 will come. So minus 460 will come, and FC and FC will get cancelled. We will get 40 to center around 40, and it is FC and FC will get cancelled, and you will get 540. Okay, this is when you shift it towards right. This is when you shift it towards right, like this, and this part will come here. Okay, this part is shifted here, and this part will shift somewhere here. So FC plus 40, so it is it is 2FC plus 40 and 2FC plus 540 and 2FC minus 460. Okay, so this spectrum will shift here, and the mirror image of the same signal will also come. So what will be the mirror image? The mirror image will be somewhere at minus 540. We will get somewhere at minus 540, and this signal will come here also, minus 540 and minus 540 and plus 460. So let us say plus 460 somewhere here. This is plus 460 and this is your minus 40. So it is centered on minus 40 and it will be shifted here, and one more term will come, which is this one. This will shift somewhere here at minus of 2FC plus 40. Now we have a low pass filter which is having the cutoff frequency 510. So it will allow the frequencies which are less than 540, 510. So the frequency component which is less than 510 will be this. The frequency component which is less than 510 will be the frequency which is at minus 460 and plus 460. Okay, minus 460 and plus 460, and the amplitude is half here because you are shifting again now. So when you will shift again, the amplitude become half. So how will you write this expression? So the expression you will write, the expression of this output of the low pass filter will be looking like this. Okay, the output of the low pass filter is this one only. The amplitude gets half. Okay, the amplitude gets half, and this is 460 and minus 460. So how will you write this expression? So this output, which we have denoted it as yt. So the Fourier transform, this is y of f. What is y of f? So y of f is 1 by 2 impulse at 460. So f minus 460 plus 1 by 2 impulse at plus 460. So f plus 460 here, right? Now, if we take the inverse Fourier transform, taking inverse Fourier transform, this y of t will become cos of 2 pi into frequency. What is the frequency? 460 t. So we can write this as cos 920 pi t. So cos 920 pi t would be the right answer for this. Yes, option B, cos. Yes. Okay, so this is how you have to approach. There may be a direct relation you can solve by mathematical expression also you can solve. No issue with that. You can directly write the mathematical equation. That means you have to multiply this x of mt cos 2 pi fct with this cos 2 pi fct, and this is also cos. So there are three cos terms that you need to multiply, and after that multiplication you can choose the appropriate frequency to get the desired output according to the filter. So that's usually can be done. So that's why I have taken some different approach, and that different approach I have taken the spectrum approach. So suppose I would have drawn the spectrum, then I would have got this result. Okay, this is the Fourier transform of, let us say, zt. So zt, and this you will get. Okay, this is z of f. Okay, got it? Now coming to the next topic, this was all related to modulation. If you have understood the modulation, then you can easily solve this type of questions where they ask you to calculate the bandwidth, they ask you to calculate the spectrum, they ask you to calculate what will be the waveform in the output, what are the frequency component you will get after passing through the filter. So these are the basic things that you should know about the signal, because communication means you can say that that was nothing but a question from the signals. We haven't started the concept of the communication. That was purely based on the concept of Fourier transform. If you know the Fourier transform, you can easily solve this type of question. Now coming to the amplitude modulation. अनंत कहाँ पे मैग्नीट्यूड 1 होगा बोल रहे हो? ये मैग्नीट्यूड तो 1/2 होगा, ये वाला मैग्नीट्यूड 1/2 होगा ना, बिकॉज यहाँ पे देखो पहले 2 हुआ, फिर 1 हुआ, फिर एक बार और आपने फोरियर ट्रांसफॉर्म लिया है तो 1/2 हो गया, मतलब शिफ्टिंग किया है। ठीक है, देखो पहले आपका एम्पलीट्यूड 4 था, तो जब आपने कॉस का फोरियर ट्रांसफॉर्म लिया तो वहां से एम्पलीट्यूड हाफ हो गया, तो ये 4 से 2 हो गया। फिर आपने फिर से कॉस से मल्टीप्लाई किया, तो कॉस से मल्टीप्लाई किए तो शिफ्ट हुआ, तो फिर ये 2 से 1 हो गया। फिर एक बार और कॉस से मल्टीप्लाई, क्योंकि टोटल 3 बार कॉस से मल्टीप्लाई हुआ है, तो फिर एक बार और मल्टीप्लाई हुआ तो वो हो गया 1/2। फिर ये एम्पलीट्यूड 1/2 हो गया, तो यहाँ पे 1/2 के हिसाब से लिखोगे तो उसका इनवर्स फोरियर ट्रांसफॉर्म लोगे तो यहाँ पे एम्पलीट्यूड 1 हो जाएगा। ओके, ठीक है। नाउ कमिंग टू द एम्पलीट्यूड मॉड्यूलेशन, इट इज द प्रोसेस इन व्हिच द एम्पलीट्यूड ऑफ द कैरियर। नाउ अब हम लोग क्या करेंगे कि कैरियर के एम्पलीट्यूड को वी विल चेंज अकॉर्डिंग टू द मैसेज सिग्नल, है ना। अकॉर्डिंग टू द मैसेज सिग्नल एवरी इंस्टेंट amplitude message signal can have the different amplitude. So every instant of amplitude of message signal we will change the amplitude of carrier signal. What is our carrier signal? Carrier is a cos signal, so the amplitude of this carrier, that is cos, we will change according to the message signal. We will get the output s of t, which is written as AC 1 plus k into mt and cos omega ct. So that would be our output, है ना। जब भी आपको एम्पलीट्यूड मॉड्यूलेटेड सिग्नल बोले, you have to look for this type of expression, 1 plus k mt cos omega ct, that is your carrier signal, amplitude modulated signal. So the expression we have written where AC is carrier amplitude, k is amplitude sensitivity of the modulator, जिसका यूनिट होता है आपका वोल्ट इनवर्स। ठीक है, now the mt is message signal, cos 2 pi fct is your carrier frequency. Now except this cos, we will have AC 1 plus k mt, that is known as envelope of the signal. Okay, envelope of AM signal. So what is now modulation index? There is one important parameter that is associated with this amplitude modulation, that is known as modulation, because whenever we perform the modulation, how much modulation we have performed, that is to be measured, and to measure this we have a modulation index. So it is a measure of how much a modulating signal modulates the carrier signal, up to which depth it is modulating our carrier signal is called the depth of modulation or modulation index. Okay, so how much you are mixing your message signal in the carrier signal. Okay, when we do perform some experiment, we mix suppose one chemical with the other. So that means how much percentage or how much concentration we are mixing for the second chemical, right? So that is how we are saying that we have the two different signals and we are mixing the message signal in our carrier signal. So how much we are mixing, up to which depth we are mixing, that is called the modulation index or depth of modulation. So modulation index MA is equal to K into maximum value of MT. So that is your modulation index. This is the general formula which can be applied anywhere. And for single tone modulation, the message signal amplitude is 1 AM. So if the message signal amplitude is AM, then the maximum value of message signal is AM. So K into AM is the modulation index for sinusoidal signal. Yes, in general, the modulation index is always K into. Now, yeah. Now, if I suppose want to calculate the how much bandwidth is required in AM signal, because there are certain parameters that we need to discuss. First, about the if we modulate. Okay, in communication, we only focus on the two important thing in the analog communication. First is the how much power is required, and second is the how much bandwidth we are going to use. So first thing that we have to see is bandwidth. So to calculate the bandwidth, what you will do, you will put this message signal in our standard expression where MT was AM cos omega mt and then cos omega ct. So this is modulation index. So AC 1 plus modulation index cos omega mt into cos omega ct. So when we expand this, okay, when we expand this, we will get AC cos omega ct, AC ma by 2 cos 2 pi fc plus fmt, cos a plus b and cos a minus b, that is fc minus f. So this is known as the carrier term. Okay, that is known as carrier term. This is known as a high frequency term. So this is high frequency, or you can say frequency higher than the carrier. So that is known as upper sideband, and this fc minus fm is lower sideband. Okay, so this carrier term we will draw when we take the Fourier transform. We will draw it here. The amplitude gets half, which is fc, and then the carrier frequency fc plus fm. So this is fc plus fm, and this fc minus fm. This is fc minus fm. So whatever we draw in the positive side, the mirror image comes in the negative side. So just by looking into the frequency, you can draw the right hand side, that is the positive side, and then draw the mirror image. That is it. So this is your lower sideband, this is our upper sideband, and this is the carrier term. So when I calculate the bandwidth is, because this is a band pass signal, so bandwidth will be calculated only this. You will not calculate the bandwidth from origin, because our information lies on this range only. You should not be calculating the bandwidth from the zero. Okay, it will be from the band, because when we modulate, we have got the band pass signal. So that band pass signal will have the bandwidth equal to twice of fm. So message signal will be having the bandwidth 2 times of fm. Now when we talk about the time domain expression, that how do we analyze in the time domain. So in the time domain, the standard expression for single tone, we will have AC 1 plus MA cos 2 pi FM cos 2 pi FC. Just now we have seen. After that we had taken Fourier transform, because we wanted to analyze in the frequency domain. Now we will not take Fourier transform. We will analyze from here. What is the envelope of this? So I told you that except this carrier signal, the remaining term is called envelope. So this is envelope, and when we put this value AC 1 plus MA cos 2 pi FMT, the maximum value of envelope is AC 1 plus MA. The minimum value of envelope is AC 1 minus MA, depending upon the cos. The cos is as the maximum amplitude 1 and the minimum amplitude minus 1. So according to that, 1 and minus 1, you will get the maximum and the minimum. Okay. Then when you divide it and when you subtract it, you will get the some different expressions. So when you add it, you will get carrier amplitude, that is Emax plus Emin by 2. When you subtract it, you will get message signal amplitude, which is Emax minus Emin divided by 2. Okay, when you subtract it, you can see when you will subtract, you will get Emax minus Emin and 2 AC MA. So here you can write modulation index as AM upon AC. Okay, modulation index is nothing but AM upon AC. So this AC will get cancelled, and we will get 2 AM equal to Emax minus Emin. So 2 AM is equal to Emax minus Emin. So AM is equal to Emax minus Emin. Considering that the modulation index is AM upon AC. Okay, and then you can have the, after division, there is one more formula of the modulation index comes, which is also important for our exam point of view, which is Emax minus Emin divided by Emax plus Emin. That is the modulation index for AM. Now, if we have undermodulated signal, then in the undermodulated signal, we will get the shape like this, where we have, this is the maximum envelope, this is the minimum envelope. Okay, this is the minimum envelope, this is the maximum envelope. Just now we calculated this maximum and minimum envelope. In the positive side as well as negative side, this left hand side is called unmodulated carrier, because this is the signal where message signal is not applied. When the message signal is not applied, you will get the carrier signal as it is. The carrier signal will be oscillating between the plus AC and minus AC. So once you apply the message signal, suddenly the carrier amplitude will have increased. Carrier amplitude will be increased. So when the carrier amplitude will be increased, then after that, once you apply the message signal, after that, the carrier amplitude will change according to the message signal. So this is our message signal. This is our message signal. So this is nothing but called a envelope of message signal. Okay, that is called envelope of message signal. Now critical modulation is modulation index equal to 1. So critical modulation, when the modulation index is equal to 1, then the lower envelope, minimum envelope will touch this axis, and you will getting the shape like this. Okay, and when the modulation index is greater than 1, then minimum envelope is going downward. So as you start increasing the modulation index, the minimum envelope goes downward, and when you are increasing the modulation index greater than 1, then it will be reaching towards the negative side. So it will be reaching towards the negative side, and apart from this, you will be getting the phase reversal where this envelope is crossing the 0. So this is called the phase reversal effect. Phase reversal you get at the point where the envelope crosses the 0. Okay, which is not desirable, because at the receiver we will be using the envelope detector, because there are multiple receivers than the transmitter. Like suppose in the FM station, if you talk about, then there are thousand and lakhs of crores of the people who are listening this FM broadcast or AM broadcast. So there are multiple receivers, but we have to transmit the signal from one transmitter in one city or one location. Okay, in particular area we will be having one radio station, or maybe maximum of 2 radio stations if there is a large geographical region. So there are receivers are many and the transmitter are only one. So transmitter can have the complex design, but the receiver should be very cheap and very simple design, so that it can be easily designed and it can be easily applied to any device. So if it is cheap, then it can be applied to any device and the system will become overall cheap. Hence, we don't want our modulation index to be greater than 1, because in the detection of amplitude modulation, we will be using the envelope detector, and the envelope detector is a simple diode based circuit, and diode is easily available. Hence, and the diode works only in the positive cycle of the signal, so it is not going to generate your it is not going to generate the proper signal if this is over modulated. Okay, if the signal is over modulated, then it is not going to generate this negative half of our original signal. Hence, we will not be using this modulation index greater than 1. Now, what is the order of the bandwidth? If I say, then the order of the bandwidth for the SSB is very less, and then VSB and the double sideband suppressed carrier and the double sideband full carrier uses the same bandwidth. Double sideband full carrier uses the 2 FM, suppressed carrier also 2 FM, single sideband FM, and vestigial sideband just little bit more than the FM. Now, what is the order of power? So, power requirement, what is the power requirement? So, let us understand what is the power requirement first. Okay, so the power requirement for a single tone, sinusoidal, the power requirement, the carrier power is given as AC square by 2R. Okay, and the upper sideband power is equal to the lower sideband power, and that is nothing but the AC square MA square by 8. Okay, which can also be written as 8R, and which can also be written as PC into MA square by 4. So the total sideband power is given by the total sideband power. The total sideband power is nothing but the PSB we represent, and it is the sum of upper sideband plus lower sideband power. Because both the sideband has the same power, so it is PC into MA square by 2. Okay, and the total transmitted power, which can be generated here, is PC 1 plus MA square divided by 2. R is the resistance, R is the load resistance. Like sometimes it may be an antenna resistance. Okay, if it is given, then use it. If it is not given, then use 1 ohm. Okay, if not given, if R is not given in the question, then we take R is equal to 1 ohm. Okay, then R is equal to 1. So this is the formula, and the transmission efficiency is nothing but the useful power divided by total power. Okay, useful power divided by the total power. So what is the useful power and the total power? So after calculation, 2 MA square upon 2 plus MA square comes हाँ स्क्वायर और ट्रायंगुलर के लिए देखो यहाँ पे स्क्वायर और ट्रायंगुलर वैसे तो कभी आता खास है नहीं, है ना। तो बेटर क्या है मालूम है कि बेटर ये है कि यू राइट इन टर्म्स ऑफ जनरल फॉर्मूला, है ना। तो ये तो आपका साइनसॉइडल के लिए हो गया, और जनरलाइज्ड करना है ट्रायंगुलर के लिए यहाँ पे 3 आ जाएगा। ठीक है, इसी फॉर्मूले में अगर यू आर राइटिंग फॉर ट्रायंगुलर, तो ट्रायंगुलर के लिए दैट विल बिकम MA स्क्वायर अपॉन 3 प्लस MA स्क्वायर, एंड स्क्वायर के लिए इट विल बिकम MA square upon 2 plus MA square. Sorry, 1 plus MA square. Okay. हाँ जनरल यूज कर लो, बेटर है। व्हाट इज जनरल फॉर्मूला? द जनरल फॉर्मूला, जैसे कि वी हैव ए जनरल एक्सप्रेशन दैट इज AC 1 plus K into MT then cos omega CT. This is our general formula. So from here you can write the efficiency in general, which is K square the signal power divided by 1 plus K square into signal power. सिग्नल पावर आपको निकालने आता है फ्रॉम द सिग्नल्स एंड सिस्टम, है ना। कोई भी सिग्नल दिया हो, एनी रैंडम सिग्नल, इफ इट इज गिवन इन द क्वेश्चन, then you know that how to calculate the power. है ना. So Sx is nothing but the average signal power. So average signal power you can calculate by using 1 upon time period integration over the time period, and if the signal is empty, so empty mod square dt. यहाँ से आप कैलकुलेट कर सकते हो सिग्नल के कॉन्सेप्ट से, और जस्ट यहाँ पे सब्स्टिट्यूट कर दो, यू विल गेट द एग्जैक्ट आंसर. तो आपको कोई फॉर्मूला याद रखने की जरूरत नहीं है. मे बी हो सकता है कि ट्रायंगुलर में वो हाफ वेव, आपको ट्रायंगुलर का आपको कैसा ट्रायंगल दिया है जिसमें आपका पावर 2a² by 3 आ रहा है या a²by 3 ले रहे हो, उसके अकॉर्डिंग थोड़ा सा चेंज हो जाएगा, है ना. लाइक इफ वी यूज है ना सिग्नल पावर फॉर ट्रायंगल, है ना. जैसे कि फॉर ट्रायंगल है तो ट्रायंगुलर सिग्नल के लिए सिग्नल पावर क्या होता है. सो वी कैन राइट am²by 3 ऑल्सो, है ना. am²by 3 लिख सकते हैं. So am²by 3 if you will write, then you will say k² am² divided by 3 plus upon 1 plus k² am² divided by 3, and k into am will become the modulation index. So modulation index, so this is ma² divided by 3 plus ma². Okay, so if you suppose write 2am²by 3, if you write the 2am²by 3, then it will become 2ma², because somebody may confuse that कि आपका ट्रायंगुलर सिग्नल कैसा है ना. somebody may get confused कि ट्रायंगुलर आपका वेवफॉर्म कैसा है, किस केस में आपको 2am²by 3 लेना है. कई बार हाँ, ये देखो कुणाल ने बोला हाफ ट्रायंगल के लिए am²by 3 होता है, बट फुल ट्रायंगल के लिए 2am² होता है. तो जब यहाँ पे 2am² लिखोगे तो यहाँ पे 2am²by 3, यहाँ पे भी 2am²by 3, तो आपका जो फॉर्मूला है वो कितना हो जाएगा 2ma²/3 + 2ma². ठीक है, तो इसीलिए आपको ये चीज थोड़ा ध्यान रखना पड़ेगा, है ना. तो ये चीज आपको ध्यान रखना पड़ेगा. तो इस चीज को अगर आप बहुत अच्छे से जानते हो देन वेल एंड गुड. अगर आपको नहीं पता है तो बेटर है कि आप यूज करो जनरलाइज्ड फॉर्मूला, है ना. तो अगर आपका सिग्नल कॉन्सेप्ट अच्छा है, हाँ, sometimes they give unsymmetrical also. So if it is unsymmetrical etc is given, then be careful and how to write the efficiency in the amplitude modulation. Then this is the main formula. Then you calculate the power as you want, means whether you want to use the formula or you want to use the direct relation of power, that is up to you. सो इसी तरीके से हम बोले कि पावर किसमें किसमें कितना लगेगा. तो डबल साइडबैंड फुल कैरियर में सबसे ज्यादा पावर लगेगा, बिकॉज वी विल बी ट्रांसमिटिंग ऑल द 3 सिग्नल्स, है ना. डबल साइडबैंड फुल कैरियर यानी कि एम्पलीट्यूड मॉड्यूलेशन में हमको कैरियर को भेजने के लिए पावर चाहिए, अपर साइडबैंड को भेजने के लिए पावर चाहिए, लोअर साइडबैंड को भेजने के लिए पावर चाहिए. ओके, एंड देन डबल साइडबैंड सप्रेस कैरियर के लिए लोअर साइडबैंड को भेजने के लिए पावर चाहिए, अपर साइडबैंड को भेजने के लिए पावर चाहिए. Single sideband, only you need only one sideband power, either you will transmit the upper or lower. So similarly, in this way we will write the sequence of the power, that which one will use least power and which one will use the maximum power. ओके, सो पावर का डिस्कशन हम लोगों ने कर लिया है. ac²/2, देखो यहाँ पे r नहीं लिखा है, तो कई बार r नहीं लिखा होगा. सो इफ r इज नॉट गिवन देन r इज इक्वल टू 1 ओम. पावर को हम लोग कन्वर्ट कर सकते हैं इन द टर्म्स ऑफ वोल्टेज एंड द करंट. सो vt इज इक्वल टू vc √1 + ma²/2 and it is equal to ic 1 + ma²/2. So these are the vt and it. Okay, so here also we have seen this ma²/2 + ma². the efficiency, जैसे जैसे मॉड्यूलेशन इंक्रीज करोगे, है ना, जैसे जैसे मॉड्यूलेशन इंडेक्स इंक्रीज करोगे तो एफिशिएंसी इंक्रीज होती जाएगी. सो मोनोटोनिकली फंक्शन, सो efficiency is monotonically function of a modulation index. So as you increase the modulation index, the efficiency will also increase. The efficiency would be 0.5, say 11.11, then 20%, then 33. So modulation index, when the modulation index is 1, which is the largest value, the efficiency is 33. The efficiency is 33. Sorry. Yeah, table is nothing but I am changing the value of modulation index from starting from the 0.1, 0.5, 0.707 and 1. ठीक है, बस यही मैं कर रहा हूँ. तो यहाँ पे क्या कर रहा हूँ, आपके लिए इंपॉर्टेंट पैरामीटर, इसमें इंपॉर्टेंट वैल्यूज कौन से, ये तीन वैल्यू के रिजल्ट अगर आपको याद रहेंगे तो बहुत सारे क्वेश्चन में आपको हेल्प हो जाएगा. ठीक है, तो 0.1 का तो चलो 0.5% आ गया. देन जैसे ही आप इसको 0.5 करोगे, मॉड्यूलेशन इंडेक्स जब 1/2 होगा, बहुत सारे क्वेश्चन में यू विल सी दैट मॉड्यूलेशन इंडेक्स इज 1/2, तो उसमें आप एफिशिएंसी 11.1, 0.7 करोगे तो 20%, 1 करोगे तो 33.3%. so that is your modulation index. Modulation index versus ट्रांसमिशन एफिशिएंसी. और ट्रांसमिशन एफिशिएंसी को और क्या बोलते हैं, तो पावर एफिशिएंसी वर्ड भी कई बार यूज करते हैं. So power calculation in general we have done. These are some in general formula. Now what is power saving? The power saving in double sideband suppressed carrier. So let's calculate the percentage power saving. Okay, so the percentage power saving is how much power you have saved. Recently they in the gate they asked the question related to the power saving. So power saved divided by total power which we are using to transmit, multiplied with 100. So how much power we saved in the double sideband? By suppressing the carrier we saved the carrier power. So and then PC 1 plus MA square by 2 multiplied with 100. So this PC and PC will get cancelled. So 2 upon 2 plus MA square into 100. That is the formula of the percentage power saving. Now what is the percentage power saving in the single sideband? So percentage power saving. How much power we saved in the single sideband? We saved the power of, let us say, upper sideband. Okay, let us say we are saving the power of upper sideband plus power of carrier. That means we are transmitting the lower sideband power. So if you are transmitting the lower sideband power, then how much power you are saving? That is what we need to write here. So what is the carrier? Carrier power is PC, and what about the upper sideband power? This is PC MA square by 4. So this is PC 1 plus MA square by 2 into 100. So PC is common and it will get cancelled. So we can write 1 plus MA square by 4 and divided by 1 plus MA square by 2 multiplied with 100. So in this way, the percentage power saving can be calculated. So power and the bandwidth calculation of AM for multi-tone signal, we will have more than one message signal and frequency, more than one message signal frequency. So if this is multi-tone, then we have to choose the bandwidth by calculating the highest frequency of all the frequency component. So whatever message signal frequency you have, choose the maximum frequency, then twice of that will be the bandwidth. And then how do you calculate the overall modulation index? So overall modulation index is the root over of square root of MA1 square plus MA2 square. Corresponding to each frequency, we will get one modulation index, and square and summation of those modulation index will give you the overall modulation index square root. Okay, and then the transmission efficiency is same as the for the single tone, that is MA square upon 2 plus MA square. Now, if you want to calculate the depth of modulation index in this case, then how do you calculate? Okay, quickly can you tell me the answer, because this is a simple question, but just for how to apply some formulas. Yes, you are getting the answer. So here we are saying that the depth of modulation index we want to calculate, but the current is given. So IT is equal to IC 1 plus MA square by 2 and root over it. So root over it, so we have a 4.8 current and the carrier current is 4. So we will square it. So we will get 1 plus MA square by 2. So MA square is nothing but the 4.8 upon 4 whole square minus 1 multiplied with 2. So it is 1.2 whole square. So it will become 1.44 minus 1. Okay, multiplied with 2. So it is 0.88 something. Root over 0.88. Root over 0.88 something. So we are getting 0.938, or you can say 93.8%. Yes, option A was right. Option A was right. Yes, Kunal. Now, what is the percentage power saving in this case for double sideband suppressed carrier? Double sideband suppressed carrier. Double sideband suppressed carrier. Power saved divided by total power minus V. Just now I discussed that for the double sideband suppressed carrier we have a percentage power saving formula. Okay, that percentage power saving formula we have calculated, that is nothing but the 2 upon 2 plus MA square, which is power saved divided by total power. So power saved divided by total power. So the power saved is how much power you saved, the carrier power you saved. What was the total power? 1 plus MA square by 2. Okay, multiplied with 100. So from here you will get 2 upon 2 plus modulation index square into 100. Put the modulation index, which is 80. So 2 upon 2 plus 0.8 square into 100. 2 upon 2 plus 0.8 square into 100, you will get 75.76. That is the right answer. Yes. Yes, perfect, Purni. Shruti, why you are getting option B? Surendran, why you are getting B? Which formula you are using and getting B? Already see the modulation index is 80, then how can be the power saving will be 80 itself? Huh? It is double sideband suppressed carrier. If suppose it is written that double sideband full carrier, then there is no power saving, because it is double sideband full carrier. So in double sideband full carrier we have to transmit all the power. So no power will be saved. So that case we would have said option A, nil. Nil will come when the double sideband full carrier would have been written. Then if suppose double sideband full carrier is written, and then for any modulation index the power saving will be nil. Power we save when we perform some other type of modulation in the AM, like double sideband suppressed carrier, single sideband suppressed carrier. These are the two standard, because here we can calculate the power. Yes, then 0%. Yes. Now what is the modulation index in this case? Yes, so it is option C, because we know that the modulation index is having the formula Emax minus Emin divided by Emax plus Emin. So it is 125 minus 25 divided by 125 plus 25. So it is 66.6%. What will be the expression for this? The same waveform, what will be the expression? Yes, just we need to calculate the carrier amplitude. The carrier amplitude is Emax plus Emin divided by 2. So it is 125 plus 25 divided by 2. So it is 75 volt. Yes. So the rest of the things we are same only. The two things we want, the carrier amplitude and the modulation index. The modulation index we calculated in the previous part, and the carrier amplitude. What is the answer of this question? We want to calculate the amplitude and phase of additional carrier. Amplitude and phase of additional carrier, so that the modulation index will be 20% now. So previously the modulation index was 66.6%. Previously the modulation index was 66.6%. Now we want the modulation index 20%. how do you calculate this additional carrier? So this additional carrier can be calculated because we have already AM signal, right? We have additional carrier. Yes. So additional carrier, see how to solve this. First of all, we were having the amplitude modulated signal, which is 75. 75 was the carrier amplitude. 1 plus 2 by 3 is the modulation index, and cos omega t into cos omega ct. Okay, that was our signal. Now we want to add additional carrier. Additional carrier means if it is saying only carrier, that means it is asking for the carrier frequency. So we have to take the same carrier frequency, and it is asking for the additional carrier amplitude. So that means the amplitude will be different from the previous carrier. The previous carrier was having the amplitude 75, but now the additional carrier which we are adding should have the same frequency which we used previously, but the amplitude would be different. So now if you will write it, you will get 75 plus a cos omega ct into 75 into 2 by 3 cos omega mt into cos omega ct. Okay, so now if I suppose take common to convert it in the standard form, then it is 75 into 2 by 3 cos omega mt divided by 75 plus a in bracket cos omega ct. So what is the modulation index then? The new modulation index will be 75 into 2 by 3 divided by 75 plus a. So it is said that it is having the 20%. So 20% means you can write this is 150 divided by 3 into 75 plus a, and 20% means 20 upon 100. So this can be 50 and this can be 5. So it is 250 equal to 75 plus a. So 75 plus a. So a is equal to 250 minus 75 is equal to 175. So 175 amplitude is required and it is coming positive. So hence we will say that 175 volt at an angle 0, because it is coming positive now. So the phase is only 0 or 180 degree. That means the phase will be either 0 or 180, means the value will be either positive or negative. So it is coming positive. So hence answer is 175. 175 volt would be the right answer. Okay. Have you understood the approach? So in this type of question, first of all, if it is saying that only carrier is added, that means you have to take the carrier frequency, not the amplitude. Okay, because it is asking to calculate the amplitude of carrier. It is asking for the calculation of carrier. It is asking for the calculation of carrier. Yes, now answer this question. Yes, because here the message signal amplitude modulated by symmetrical square wave. So this is carrier signal is modulated. The carrier signal is amplitude modulated by symmetrical square wave. So this is our message signal. So message signal is symmetrical square wave, and symmetrical square wave will have only odd harmonics. Okay, because it will have only odd harmonics, the frequency it will generate is FM. Okay, that is our message signal frequency. Then FC plus 2 FM, sorry, 3 FM plus minus 3 FM, because only odd harmonics will come. So FC plus minus FM, and then FC plus minus 3 FM will come. Then FC plus minus 5 FM will come. So these are the frequency which will be generated. So FM means how much the fundamental time period is 100 microsecond. So it is inverse. So it is 10 kilohertz. Message signal frequency is 10 kilohertz. So it is 1000. This is 1000 kilohertz. So 1000 kilohertz plus minus FM, that is 10. So how much it is? 990 and 1010. It will be generating in kilohertz. Then from here it will be 1000 plus minus 30, 3 FM. So it would be generating 970 kilohertz and 1030 kilohertz. So it is generating all this frequency. So when you will calculate here the 1050 kilohertz, 950 kilohertz. So it is saying that which one will not be present. So not be present means 1020 will not be present, because it will come when there is a even multiple. Because the even multiple is not present, then it will not have the even multiple. So answer C. Yes. Yes. So we have the two type of generation scheme, that is the switching modulator and the square law modulator. And in the square law modulator we have the nonlinear device. This nonlinear device will have some characteristics, and passing through these characteristics we get YT, and when we pass it through the filter we will get our band pass filter output, which is a desired AM signal. Okay, and a square law modulator in standard form, when you have the output and the input characteristics. Okay, when the output and the input characteristics is A1 VIT plus A2 VI square T, then we get this output. So you have to remember this formula, but you also have to take care of selecting this formula when the value of the nonlinear device, the characteristic of the nonlinear device is this. Then only you can use this formula. So this is important formula. Whenever the expression is given in this form, that is only the linear term and the square term is given, then you can choose this formula. And also when we take the square law modulator, we have the carrier frequency much greater than 3 FM. When the switching modulator we talk about, we have a diode in series with the message and the carrier, and then the output we get is the band pass filter. So these are the two methods. So these are not that much important. Yes, important thing about the switching modulator is that the carrier frequency which is required in case of switching modulator is just greater than 2 FM, which was in the square law modulator 3 FM. Okay, can you answer this question? Square law plus switching, it never come like that. Switching and square law, we cannot add them. These two are different methods, so there will be no addition kind of thing here. Yes, option D will come, because here the standard expression of square law modulator is given. So the K is equal to modulation index, which is 2 into A2 by A1. So here the square term is having value b, so 2b by a. So this is given as a by b is equal to 2 upon ka. We want to calculate a by b. So a by b is 2 by ka. Now we have to calculate the modulation index. Modulation index is k into message signal amplitude. Here message signal amplitude is 1. So k equal to 1. K equal to ma. Okay, that means ma equal to ka. And here also given that the sideband power is half of the carrier power. The ratio of sideband power to the carrier power is also given as ma square by 2 for single tone, which is m 1 by 2. So modulation index is 1. So modulation index is 1. Since the modulation index is 1, the value of k is also 1. So value of k is 1. That means a by b is 2. So answer is option D. Yes. The option will be option. The answer will be option D. The sideband power to the carrier power is ma square by 2. Modulation index is 1. And modulation index formula we have seen k into am. Am is 1 because the message signal is having amplitude 1 here in this question given. And then modulation index is 1. So k will become 1. And then by the formula we get a by b is equal to 2. Okay, now the detection of AM. The detection of AM can be applied for the three different conditions. When the modulation index is less than 1, it is called a square law demodulator. When the modulation index is greater than 1, theoretically we can use synchronous detector, and envelope detector will be mostly used when the modulation index is less than equal to 1. The condition for the square law demodulator is nothing special about this. Yes, one more thing that is for a square law demodulator, the modulation index should be very less than 2. Okay, if you want to recover your message signal using the square law demodulator, then the modulation index should be very less. That means around 20 to 25%. And a synchronous detector is no use here. Analog detector will be using the charging discharging concept, where you have to remember about the proper envelope detection. So for proper envelope detection, the time constant should be greater than 1 upon fc and less than 1 upon fm. If the time constant is less than 1 upon fc, then the carrier, the capacitor will get discharged very fastly before the time period of the carrier, and the envelope will not be followed by the capacitor voltage. And when the time constant is greater than 1 upon fm, then the discharging is too much slow that the capacitor voltage does not follow the envelope. It misses this peak values of the envelope, and hence it is called diagonal clipping. It is called the diagonal clipping. When the capacitor voltage is not able to follow, it discharges very slowly, even the less than the time period of the message signal, then it misses this sum of the message signal peak values, which are known as diagonal clipping. And when the modulation index greater than 1, then the over modulated signal, that means the minimum envelope will go in the negative half, and in the negative half we will not be able to follow the envelope again, because the diode will not work in that region. So envelope detector, whenever you give input to the envelope detector like a sinusoidal signal, you get a flat response, that is the DC signal, because for a sinusoidal signal like this, the envelope is the DC signal. This is the envelope. So when you will choose the proper time constant, then your capacitor will follow this path, charging, discharging, and hence you will get the flat response. And when you give the modulation index less than 1, when you give AM signal with modulation index less than 1, then your output will be proportional to the message signal. And when the modulation index is greater than 1, then your output will be mod of envelope. So you will get something, but it is mod of envelope. Yeah, so can you answer this question? Yes. So here the answer is 2 because the modulation index is coming here is 2 by AC, and the modulation index should be very less than should be less than equal to 1. So less than equal to 1. So AC is greater than equal to 2. So the minimum value of AC is 2. Yes. So the right answer is 2. Now to generate the double sideband suppressed carrier, we have balance modulator, we have ring modulator. The balance modulator block diagram is not required. For ring modulator, this is the kind of circuit you will be able to see. The diode is connected in the form of bridge, and during the positive half cycle, the diode D1 and D2 will work, and for the negative half cycle, diode D3 and D4 will work. And in this case, in the ring modulator, the carrier signal is mostly a square wave. So that is the square wave. Okay, so that part is you might be knowing about. Okay guys, so you should be aware about this thing that this is the schedule of the upcoming revision marathon. So this is a communication system which is running, and power system for electrical. 13th January EDC will be running at 4 p.m. and the rest of the subjects will start from 10 a.m. only. So we have phase. There are three methods to generate the SSB signal: filter method, phase shift method, and reverse method. Reverse method is also one of the methods to generate the single sideband. This will be useful when there will be a matching type of question comes. Okay, which is very rare in the GATE examination. So let's come into the. Yeah, can you answer this question? Yes, so answer is option D, because when you solve it, you will get multiplication of here. So you will get mt into cos omega naught t and cos omega naught t plus theta. So 2 cos A cos B formula will be applied. So mt by 2 cos omega t plus theta, this is cos A plus B. And when cos A minus B will be performed cos theta, so we will be getting the output as mt by 2 cos theta. That is our output. Now we want to calculate the power. So power will be m squared t whole bar divided by 4 into cos theta. Power of message signal is given as pm cos theta by 4. Pm cos square. When you square, cos is square also. Amplitude is square divided by 2. So like that we can do, or you can simply calculate by squaring it. Yes, option D. Option D will be the right answer. Yes, what is the answer of this question? Yes, because we know that when we perform the Hilbert transform, energy does not change. So energy is not going to change. So energy of input and its Hilbert transform will be same. So what is the energy of input? So that is nothing but the amplitude is square divided by 2 into the energy, which is 1. So it is 16 upon 2, which is 8. So energy of input will be 8. So our energy of output will also be 8. It is not a square by 2. It is actually it is actually if the energy of the sink is 1, then it is suppose the sink T is having the energy E, then it is like K into sink alpha T will have energy K square E upon alpha. So that is to be applied here, and energy of sink is 1. Energy of sink is 1. Okay, so energy of sink is 1, so that is why K square means 4 square by 2, alpha is 2 here, and the energy is 1. Now we will come angle modulation. Now let's start with the angle modulation. Just let's take 5 minutes break. Okay, let's take 5 minutes break. You can also take 5 minutes break, means you can go around, you can take water and all. Then we will start the session in the 5 minutes. Okay, this is around 6:51 in my watch, and 6:55 we will be starting. Okay, in 6:55 we will be starting. Sorry guys for the little bit delay actually because there are some construction work also running. So he wanted to ask something, so it took some time. ठीक है, तो कुछ कारपेंटर वर्क चल रहा है। हाँ, आपको बीच बीच में आवाज भी आता होगा, तो थोड़ा साइड में आवाज आ रही है, वो काम चल रहा है, तो वहाँ पे कुछ कुछ डिस्कशन कर रहे थे, तो वो उनको कुछ पूछना था कुछ फाइनल करने से पहले, तो उसमें टाइम लग गया। ओके, सो लेट्स स्टार्ट द एंगल मॉड्यूलेशन। सो एंगल मॉड्यूलेशन की डेफिनेशन तो आपने पढ़ लिया होगा, है ना। नाउ लेट्स स्टार्ट विद द जनरल एक्सप्रेशन ऑफ द एंगल मॉड्यूलेटेड सिग्नल which is given by s of t is equal to ac cos theta or ac cos omega ct plus phi, है ना। तो phi is the phase of the carrier and omega c is the angular frequency of the carrier. So whenever we want to write the expression of angle modulated signal, we take the simple AC cos omega ct plus phi. Now there are three important parameters which is associated with the angle modulated signal. So in the general expression, the an angle modulated signal, in the general expression for the angle modulated signal is defined as theta is equal to omega ct plus phi. The instantaneous frequency Fi is equal to Fc plus d phi by dt 1 upon 2 pi. So Fi is equal to Fc plus 1 upon 2 pi d phi by dt. So whenever you want to calculate the instantaneous frequency for any angle modulated signal, then just reach out to the value theta. So once you get the value theta, just differentiate the theta and divide it by 2 pi. So this is how you can calculate your instantaneous frequency for any signal. Now we have a frequency deviation. So when you subtract the carrier frequency from instantaneous frequency, when you subtract the instantaneous frequency by the carrier frequency, that is Fi minus Fc, you will get delta F is equal to 1 upon 2 pi d phi by dt. So Fi is equal to Fc plus delta F, and instantaneous frequency will be maximum when Fc plus delta F max, and instantaneous frequency will be minimum, which is Fc plus delta F min. So maximum and minimum instantaneous frequency you can calculate, which is very very important because instantaneous frequency is the main parameter which is usually asked in your gate examination. So you have to understand that how to calculate this instantaneous frequency maximum value and the minimum value. So minimum and maximum value both depend on the frequency deviation maximum and minimum value. So to maximize the instantaneous frequency, you have to add something. So whenever you are adding something to the instantaneous frequency, that means you are increasing the instantaneous frequency. So that will give you the maximum instantaneous frequency. And when you will subtract the something from the carrier frequency, then it will give you the minimum instantaneous frequency. Okay, so this is Fi max and Fi min, and there is very important parameter known as carrier swing. The carrier swing is the term which is the difference between the instantaneous frequency and the minimum instantaneous frequency. So the difference in the maximum to the minimum instantaneous frequency is called your carrier swing. And there is one more parameter which is associated with any angle modulated signal, regardless of it is a PM signal or it is FM signal, which is a phase deviation. So whenever there is an angle modulated signal, you can calculate its phase deviation, which is the maximum value of phase. Which is the maximum value of phase. So delta phi is equal to phi minus 0. Delta phi is equal to phi minus 0. That is your frequency deviation. So maximum frequency deviation will come. Now coming to the phase modulation. So how do you define the phase modulated signal? A signal will be called as a phase modulated signal when phi is directly proportional to your message signal. When you change the phase of the carrier with respect to message signal. So when you change the phase of the carrier with respect to the message signal or according to the instantaneous value of the message signal, it is called phase modulation. So phi is directly proportional to mt and phi is equal to kp into mt. So phi is equal to Kp into mt, and Kp is equal to phase sensitivity of the modulator, which is radian per volt. Okay, the unit is radian per volt. And when you substitute this value to the instantaneous frequency, the formula will become Fi is equal to Fc plus Kp upon 2 pi dmt by dt. Yes, delta phi is equal to beta, phase deviation is equal to beta also we can say. So this is the next term which will introduce, and after the frequency deviation. So once you calculate the instantaneous frequency for the phase modulated signal, here you can see that Fi is equal to Fc plus Kp upon 2 pi dmt by dt, that is slope of message signal. Okay, so dmt upon dt is the slope of message signal. So most of the time they will give you some triangular type of signal, and you have to calculate the maximum and the minimum instantaneous frequency. So you have to choose the maximum and the minimum slope of your message signal. Now, after calculating the frequency deviation, that frequency deviation, instantaneous frequency, you can just subtract your carrier frequency. So, Fi minus Fc will become Kp upon 2 pi dmt by dt. dmt by dt is nothing but the slope of message signal. So, Kp upon 2 pi maximum value of dmt upon dt, which is the maximum phase, maximum frequency deviation of phase modulated signal. So, remember that to calculate the maximum frequency deviation, after differentiating you have to take the mod of it. Okay, after calculation of the mod, like suppose your message signal is single tone sinusoidal, so it is am cos omega mt. Okay, it is am cos omega mt. Then if you suppose differentiate it, so dmt upon dt, it will be minus am into omega m sin omega mt. So before calculating this phase deviation, frequency deviation for a phase modulated signal, then you have to take mod of it. So after calculating the magnitude, you will get am into omega m. Okay, so this is dmt by dt. Now when you substitute this value here, you will get kp upon 2 pi into am into omega m, which is 2 pi fm. So 2 pi and 2 pi will get cancelled, and it is Kp into Am into Fm. Kp into Am into Fm. Okay, now the frequency deviation. Sorry, this is the phase deviation. Okay, this is the phase deviation. There is a typing mistake. So phase deviation of a PM signal is delta phi is equal to Kp into Mt max. So Kp into maximum value of Mt will give you the phase deviation. That is nothing but the value of modulation index. So generally it is equal to the value of modulation index, Kp into Am into F. Now, how do you write the expression of PM signal? So the expression of the PM signal will be the general expression of amplitude modulated signal is given by S of t is equal to AC cos omega Ct plus phi. By putting the value of phi in the general expression, this phi will become AC cos omega Ct plus Kp into Mt. And if I substitute the message signal as Am cos omega Mt, then it will become Fc plus Kp upon 2 pi dmt by dt, that we have already seen. Now you have to substitute the message signal over here, and you will get the expression of PM signal as S of t. It is AC cos of omega Ct plus Kp into Mt. Mt is Am cos omega Mt. Now, if you substitute the modulation index here, omega Ct plus beta into cos omega mt. Okay, so that is the expression of AC cos omega Ct plus beta cos omega mt. Yeah, beta is the modulation index. We will see that beta is the modulation index, which is nothing but the ratio of maximum frequency deviation to the massive signal frequency. Beta is the ratio of maximum frequency deviation to the massive signal frequency, that is written over here. Okay, so for this is FM, maximum value of massive signal. So delta F max divided by maximum value of massive signal. Hi Pranasai, yes, we will discuss that part also. Okay, now we have a frequency modulation. So when we talk about the frequency modulation, so it is nothing but the process in which can we say that the phase deviation is proportional to the message frequency. Phase deviation is proportional to the message signal frequency. No, no, you cannot say. It depends on both the modulation. In the PM, it is not. Okay, in PM, it is not. Suppose here we are calculating the PM. Wait for some time. Yeah, here. Okay, now for single tone, if you want to see for single tone, right? For single tone message signal. For single tone message signal, this maximum frequency deviation is Kp into maximum value of AM into cos omega mt. Okay, so that is nothing but Kp into AM. That is your message signal. Okay, now this is maximum phase deviation. So here you can see that it is not depending upon the frequency of message signal. It does not depend on frequency of message signal. Okay, so you can see that Vikram, that it is not proportional to your message signal frequency. Yes, odd and even harmonics are important, Manasvi. Okay. So frequency modulation, we have got delta F is equal to Kf mt because it is directly proportional to your message signal. And the proportionality constant we are using Kf, which is in the hertz per volt. So when we substitute the value delta F, which is 1 upon 2 pi d phi by dt, that is equal to Kf max. So from here, when you take this 2 pi in the right hand side and you calculate the value of phi, then it is 2 pi Kf into mt. Okay, we have got this. Delta F is equal to 1 upon 2 pi d phi by dt, right? And in the frequency modulation, delta F is equal to Kf mt. Forget about this maximum value because that is the maximum frequency deviation. But right now we want to calculate the value of phi. So d phi is equal to 2 pi Kf into mt into dt. So when you integrate both the side, you will get this value. So phi is equal to integration from minus infinity to t 2 pi Kf into m tau d tau. Okay, then when you substitute this value AC cos omega ct plus 2 pi kf integration minus infinity to t m tau d tau, so this is kf in hertz per volt, and suppose the question sometimes in the given radian per volt, kf is given in the radian per volt, that means there is no 2 pi. So remember that whenever we solve the questions or we derive the formula, whatever formula we have derived or what we are going to use, we take this as a general expression. So all the formulas which we have got is by considering that 2 pi kf. So sometimes in the GATE examination they give you this expression. So when they give you this expression, then what you can do to calculate the value of kf, just divide it by 2 pi and multiply it by 2 pi and choose the kf as kf upon 2 pi. So whatever value of kf you were using, now take it as kf upon 2 pi, then you will get the correct answer. Okay. So always remember that if they give you the expression of the FM signal in the question, then check whether it is having the 2 pi or not. If it is not having, then multiply and divide it by 2 pi. Then your kf will become kf upon 2. Then just the kf value will be changed. Otherwise, rest of the thing, the formula will remain same. So here you can see the phase deviation is nothing but the maximum value of phase. So this is the value of phase. Now you calculate the maximum value of phase, which is 2 pi kf, maximum value of minus infinity to t m tau d tau. So when you calculate the maximum value, then you can substitute the message signal amplitude. So this is 2 pi kf and am into omega. So this is 2 pi kf, and when you take a single tone, so it is am upon omega. So here you will get 2 pi kf into am divided by 2 pi fm. Okay, 2 pi fm. So 2 pi fm. So here 2 pi will get cancelled and you will get kf into am upon fm. So here you will see that in the case of frequency modulation, that phase deviation depends upon the message signal frequency. It is not directly proportional, it is inversely proportional. Madhu, for CSE, we are not expecting any revision session. Okay. For CSE, we are not expecting any revision session. So, Vikram, now you can understand that frequency deviation, phase deviation depends on the message signal frequency or not. It depends upon the modulation technique which you are using. If you are using frequency modulation, then it is depending upon the message signal frequency as well as amplitude. And if you are using the phase modulation, then it is only depending upon the message signal amplitude, not depending upon the message signal frequency. Okay, for single tone modulation, the frequency deviation is kf into mt, we said. Okay, and if we want to calculate the maximum frequency deviation, then it is kf into maximum value of mt. So kf into maximum value of mt is am. So kf into am. The modulation index is beta is equal to maximum frequency deviation divided by fm. So it will be kf into am upon fm, which will be same as the maximum frequency deviation which we calculated. So maximum frequency deviation also we calculated the same value. What is the expression? The expression of it is AC cos omega ct plus 2 pi kf integration mt dt. This was the expression. Now for single tone, okay, it is for single tone we want to write. So AC cos omega ct plus 2 pi kf, and message signal integration. So this is am upon omega m and sine omega mt. So this is AC cos of omega ct, and here we will get the beta and sine omega mt. Random process is very important, Jaswant. Without random process, there will be no gate examination. Random process and the digital communication are the most important, and every year they ask the question from the random process without a doubt. There will be no single year in the last 20-30 years, then there is no question of random process. My Telegram link is given in the description. You can check once. The phase deviation is obviously the maximum value of phase. Okay, the maximum value of phase. And what is the maximum value of phase? Here you can see the phase is beta sine omega mt. So the maximum value of beta sine omega mt. So in both the case, whether it is a PM or it is a FM, the maximum phase deviation is nothing but the modulation index. Carrier swing is the difference. Carrier swing is the difference between the maximum and the minimum instantaneous frequency. Okay, this is the difference between the maximum and the minimum instantaneous frequency. Yes. Can you answer this question? What is the answer of this question? Okay, now here we will have maximum instantaneous frequency. So Fi, because it is already given that it is a phase modulator, so Fi maximum is Fc plus Kp upon 2 pi and Am into omega m. Okay, this is because sinusoidal message signal is also given. So it is nothing but Fc plus Kp upon 2 pi into Am into 2 pi Fm. So this 2 pi will get cancelled. Fc is 1 megahertz, that means 10 to the power 6. Kp is 2. Am is 4 volt. Root mean square value is given now. So root mean square value is given. Then tell me what you will be calculating. The 4 root 2. RMS value is given. Then what is the peak value? Peak value divided by root 2. The peak value is 4 root 2. So peak value will become 4 root 2. And message signal frequency is 1 kilohertz. That means 10 to the power 3. So you have to calculate in 10 to the power 3. Yes, 1011.31. Correct. 1011.31 kilohertz something. So that is the right answer. 101. In kilohertz it is 1011 something. Okay. The RMS value is given, so you can calculate its maximum value, which is 4 root 2. Message signal frequency is also given. So this is FM. This is your RMS value. And this is your carrier frequency. So now you can answer this. Yes. Can you tell me what will be the maximum frequency deviation in this case? Yes. So in such type of question where it is written in the form of sine and cosine inside the bracket, and then you should remember this result. Okay, you should remember this result that the frequency deviation is always equal to beta 1 f1 into beta 2 f2, the frequency of this sine. And if it is cos also, then also the same result. Yes. Can you answer this question now? See here, this is one thing which is to be observed here, that there is no 2 pi here. Okay, there is no 2 pi here. So according to that, you have to solve. So the instantaneous frequency for both are same. So it is instantaneous frequency for PM is given by Kp upon 2 pi dmt by dt. Okay, and the instantaneous frequency here is given by Kf dash. Okay, Kf dash into mt. So now you want to calculate the maximum value. So because the maximum value, we will calculate this Fc and Fc will get cancelled. This Fc and Fc will get cancelled. And here you will get the Kp upon 2 pi. The maximum value of the slope here is 5. and the maximum value of slope here is 10. So we will take the maximum value, which is 10, and kf dash is kp upon 2 pi, and Massa signal amplitude is 10. The maximum value of slope is 5. Now this is 5. So this is kf. So kp upon kf we want to calculate. So kp upon kf. Yes, so kp upon kf is 2. Yes, kp upon kf is 2. This is the maximum value of slope, and this slope is minus 10. Okay, this slope is minus 10, so it is negative and it is positive. So plus 5 and minus 10. So we will take the maximum value both sides. So we will take the maximum value of slope, that is plus 5, and the maximum value of message. So maximum value of message is 10. The maximum value of message is 10. Yes, answer is 2. Okay. Yes. Now try this question. Okay, so try this question. I am just hiding myself because you will be able to see that question. Look at the question. You will be seeing all the question. The baseband signal MT shown in figure is phase modulated to generate the PM signal phi t is equal to cos omega ct plus kmt. The time is on the millisecond, and if the carrier frequency is fc is equal to 50 kilohertz and the k is equal to 10 pi, then the ratio of minimum to maximum instantaneous frequency for phase. Yes, now I think you might have already seen. So as you can see that here we want to calculate the minimum and maximum instantaneous frequency, and our instantaneous frequency maximum value will be fc plus kp upon 2 pi dmt by dt maximum value. We want to calculate the maximum value of slope. So fc is 50 plus kp is 10 pi divided by 2 pi. What is the maximum value of slopes? There are two slopes. So here the values are 3, minus 1, but the 3 is in millisecond. Okay, the time axis in milliseconds. So 3 into 10 to the power minus 3, minus 1. and here this is 1 into 10 to the power minus 3 comma 1. So the slope will be 2 upon 2 into 10 to the power 3 is the slope here, and here is minus 2 upon 2 into 10 to the power minus 3. So that means it is 1 into 10 to the power 3 with minus sign. So the maximum slope is 2 into 10 to the power 3. So we are getting 60 into 10 to the power 3, that means 60 kilohertz. And if you calculate the minimum, yes, minimum is 50 plus kp upon 2 pi, minimum value of slope. So what is the minimum value of slope? The slope is minimum when you will subtract something. So the subtraction means the negative maximum slope. So that is 10 pi upon 2 pi into your 10 to the power 3. Minus 1 into 10 to the power 3. So this minus sign has come. So 50 minus 5 is 45 kilohertz. So 45 kilohertz. So 60 divided by 45 is 3 by 4, which is 0.75. 45 divided by 60, because we want to calculate minimum to maximum. So minimum to maximum is 45 divided by 6. 45 divided by 60 is minimum by maximum. Okay. Okay, Vikram. So generally this type of mistake we do in the examination. 4 by 3 is not answer. Minimum to maximum ratio we want to calculate. Now there are two types of FM. First is called narrowband FM, another is called wideband FM. So narrowband FM is the standard form of the narrowband FM is same FM signal, but here when we convert, because the modulation index is very less than 1, narrowband FM means the modulation index is very less than 1. So when we take the modulation index very less than 1, then it is same as the amplitude modulated signal, except that the lower sideband is inverted. Here you can see this is the carrier signal, this is your upper sideband signal, and this is your lower sideband signal, and this is negative. So the lower sideband is inverted, and in case of amplitude modulation, lower sideband was not inverted. Now the phasor diagram. So this is the phasor diagram. Here we have a carrier signal. Okay, this carrier signal, and this omega c minus omega mt, that means it is in the anti-clockwise direction, clockwise direction. So it is negative. So AC beta by 2 come here when you take 180-degree phase shift, because it is negative. So it will come somewhere here, and this is upper sideband. This is upper sideband. So my upper sideband and lower sideband. This is, you will get this. So there is a carrier, and this resultant of the sideband will give you the overall resultant. Narrowband, wideband FM, there is a similarity, that is same, that is the sidebands are same, except that the lower sideband is inverted. Wideband FM means the modulation index will be greater than 1. So modulation index should be greater than 1, and the output will have the bandwidth. So wideband FM has the infinite bandwidth. Okay, ideally the wideband FM is having the infinite bandwidth, because the expression of the wideband FM comes as n equal to 1 to infinity, n equal to minus infinity to infinity, jn beta, and then cos of omega c plus n omega n beta. Okay, AC summation n equal to minus infinite to infinite, j n beta cos omega c plus n omega mt. Now when we put n equal to 0, 1 and so on, we will get the carrier, first upper sideband, second upper sideband, third upper sideband, similarly first lower sideband, second lower sideband, third lower sideband, up to minus infinite. So that is why we get ideal bandwidth as the infinity. This Jn beta is known as Bessel function. Okay, this Jn beta is known as Bessel function. Bessel function value will be given. Remember that in the Bessel function, the argument is always a modulation index. Yes, practical bandwidth is by calculation of the Carson rule. The Carson rule says that the bandwidth is two times of maximum frequency deviation plus maximum massive signal frequency. Okay, so 2 times maximum frequency deviation plus massive signal frequency equal to 2 times beta plus 1. That is known as Carson rule. Carson rule says that because to transmit any signal we cannot have infinite bandwidth, we should have the finite bandwidth. So instead of transmitting the 100% power, we transmit the 98-99% of the total power. So if we use the 98 and 99% of the total power, then the bandwidth requirement is reduced from infinity to a finite number, and that finite number is 2 times of beta plus 1 into FM, or simply 2 times of maximum frequency deviation plus FM. Now the power calculation in the wideband FM, the total power transmitted is simply AC square by 2R. Like this is case of FM. Okay, FM or PM. On the other hand, for amplitude modulation, it was this formula. Okay, so for the frequency modulation, whether it is a PM signal or FM signal, the total power transmitted is AC square upon 2R. So to transmit this much power, the bandwidth requirement was infinity. So we are not going to transmit this power. We are going to use the 98% or 99% of this total power. So if we use this 98 or 99% of this total power, then the bandwidth requirement is 2 times of beta plus 1 into F. Okay. Now, if you want to calculate the carrier power from the wideband signal, okay, like we have got this expression AC summation n equal to minus infinite to infinite j n beta cos omega c plus n omega mt. Then for n equal to 0, we get AC j naught beta and cos omega ct. Okay, since it is having only carrier frequency, okay, this term is having only carrier frequency, so that term is called the carrier component. Okay, that term is called carrier component. So this carrier component is having how much power? So power in the carrier component is AC square J naught square beta divided by 2R. On the other hand, the carrier power in case of amplitude modulation was AC square by 2R. For amplitude modulation, it was AC square by 2R, but carrier power in case of frequency modulation or phase modulation, it is AC square J naught square beta upon 2R, and AC square upon 2R is the total power in the FM signal. So AC square upon 2R is total power in FM, and AC square upon 2R is carrier power in AM. So just try to understand the difference. Okay, so can you answer this question? So we know that the message signal amplitude here is 1. Message signal frequency is 1 kilohertz. Okay, the KF is 100, KP is this. So bandwidth of FM, it is 2 into delta F max plus FM. So what is the delta F max? So for FM, delta F max is given as KF into AM. So it is KF is 100, AM is 1, so it is 100. Message signal frequency is 1, so it is coming as 202 kilohertz. Okay, now the bandwidth of PM. So bandwidth of PM is 2 times of, formula is same for FM and PM both. Okay, FM and PM both. But for PM, the frequency deviation gets changed. For PM, the frequency deviation gets changed, that is KP into AM. So KP is 10 and AM is 1, so it is 10 kilohertz. So it is 2 into 10 plus FM is 1. So it is 22 kilohertz. So 202 and 22. So that is the answer. Yes. Now, what will be the answer of this question? So we have reached to the 50 number of likes. So this like should be more than 100 till the end of the session. The session will go around up to 11 o'clock, where we will be having one break also for dinner. When you will double the amplitude, as we have seen that this depends on the amplitude of the message signal, right? This is FM also. AM is 1, KP is 10, FM is 1. Yes. So it is KP, AM, FM. So the message signal amplitude, you can see that the frequency deviation depends on the amplitude of the message signal. So if you are doubling the amplitude of the message signal, so for FM, if you are doubling the message signal amplitude, that means the maximum frequency deviation which you calculated as 100 now will become 200. Okay, and the message signal frequency is already 1 kilohertz. Now the bandwidth is 2 times of 200 plus 1, so it is 402 kilohertz. And for PM also, the message signal, the frequency deviation depends on the message signal amplitude. So maximum frequency deviation which we calculated previously is 10, now it is 20. So 20, so what is the bandwidth? It is 2 times of 20 plus 1, it is 42 kilohertz. So 402 and 42. Yeah, we have to finish the session by today only. Well, we have a limitation actually. We cannot exceed more than 5 hours, but because of the gap, means the break, we can extend up to the 6 hours. We have a limitation. PDF password is not there. I will share the PDF free of course. There is no password like for this PDF. Now, if the message signal frequency is double, then what will happen? Yes, so as you know that for FM, the frequency deviation does not depend on the amplitude of the frequency of the message signal, and we are doubling the frequency. so it will remain 100 kilohertz, but the frequency is double. So previously the frequency was 1 kilohertz, now it will be 2 kilohertz. So it will be 2 kilohertz. So the bandwidth will be 2 times of 100 plus 2. So it is 204 kilohertz. And for PM it depends upon the message signal frequency. For PM it is kp into AM into FM. So the frequency deviation will become 20, and the message signal frequency is also 2 kilohertz. So the bandwidth is 2 times of delta F is 20, 20 plus 2. So it is overall 44 kilohertz. So 204 and 44, option C. Yes, option C. Okay, guys, so we have to start the concept of random variable. So we will start the concept of random variable after the dinner. So till then, I will be sharing you very important code. This is the QR code. This is the link for quiz. Okay, link for quiz of communication system. You can scan it. Okay, you can scan it. Okay, you can scan and you can directly go to the quiz. So suppose you have taken the dinner, then you come to this session and just scan the QR code, and then you will be forwarded to the quiz of the communication system. Then appear on that quiz till after that we will start the session. So those who have taken the dinner can take this quiz, and those who want to go for the dinner, we will resume the session around 8:30 to 8:35. Okay, thank you. Okay, guys, so we are resuming the session. Just let me know whether the voice is okay. Yeah. So we will start with this vision batch. We have 2025 and 2026. This is the contact number. Here you can contact, and we will be you will be leading to the. So concept of random variable. So random variable is a function or rule by which we assign the real number to each value of sample space. So whenever we perform an experiment, there is some outcome, and the outcome, all the possible outcome is called the sample space, and each value of the sample space is mapped onto the real axis by some rule or by some function that is called the random variable. Random variable is nothing but a mapping from the sample space to the real axis. So if we suppose perform an experiment, we tossing a coin twice, then we get this head, 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 tail, tail, head, and tail, tail. These are the sample points, and when we map it by counting the number of tail, if I count the number of tail, then I get the tail number of tail 0, number of tail 1, number of tail 1, and again number of tail 2. So that is, this is mapped to the 0 because the number of tail is 0, and the lambda 2 and the lambda 3, that is the sample point. These are having the sample point real number 1 because they are having the number of tail 1, and lambda 4 is the sample point which has the sample value or sample number of tail equal to 2, and the probability of 0, probability of x equal to 0 is probability of head head, and that is 1 by 4, and probability of, agar we want to calculate the probability of x equal to 1, that is nothing but the probability of head tail plus probability of tail head. So it is 1 by 4 plus 1 by 4, which is 1 by 2. Similarly, the probability of tail tail, that is the probability of x equal to 2, is probability of tail tail, which is again 1 by 4. Now, what is the probability? So we have calculated this is 1 by 4, 1 by 2, and 1 by 4. If you want to uh, define the cumulative distribution function for any random variable, then it is given as probability that random variable x takes value less than equal to small x. So x less than x is the CDF for any random variable x. Now this is head, 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 tail, tail, head, and tail, tail. So 1, 2, 3, 4. This is the 4 values. All are having the equal probability. So these value 1, 2, 3, 4 we have taken randomly. All are having the equal probability 1 by 4. So probability x less than x. Now the cumulative distribution function. So for probability that x equal to 1 is 1 by 4, and probability for x equal to 2 is 1 by 4, 1 by 4, 1 by 4, and it is the staircase form. So if we suppose generation and detection is important, yes. I will not suggest you to leave it. From my side, it is definitely important one. It can be asked, the question can be asked from there. Less chance, but yes, it is important. For AM especially. For amplitude modulation, it is especially important. For FM, they usually don't ask, but Armstrong method is also very important. So generation of FM, when you will study, then you will study the Armstrong method, and that is actually important. Armstrong method, they have not asked the question since very long, so there will be a question from the Armstrong method in future. Okay. Now, because it is a staircase form, we can define it in terms of unit steps. So the probability of any particular random variable value of any random variable, and its probability multiplied with the shifted version of the step. Random variable can have the three types: continuous, discontinuous, that means discrete, and the mixed random variable. A random variable is said to be a continuous type if their CDF is continuous everywhere, and it can be represented by integral of some non-negative function. And discrete time if it has the finite number of jump discontinuity and have a shape like a staircase form. Mixed random variable means it will have at least one discontinuity and one range of the continuous function. So property of the CDF is the CDF should be between 0 to 1. The CDF at minus infinity should be 0, and the CDF at infinity is 1, and the CDF is a non-decreasing function. So as you continuously increase the value of random variable, the CDF value will be higher for the higher value of the random variable, or it may be equal also, and otherwise it will be less than the given value. Then if I calculate the CDF is a continuous from the right. Continuous from the right means if it is, if any function is continuous everywhere, then fx of a minus fx of a plus is same if it is continuous everywhere. And if the CDF is having the discontinuity, if the CDF is having the discontinuity at x equal to a, so fx a minus is not equal to fx of a, equal to fx of a plus. So fx of a and a plus are equal, then that is called the continuous from the right. If fx of a minus is not equal to fx of a, that it is not continuous from the left. And probability that x equal to a, suppose you want to calculate the probability at x equal to a, then it is fx of a minus fx of a minus, and the CDF is continuous everywhere. At a probability at x equal to a, it is 0, and the CDF is having the discontinuity at x equal to a. So probability at x equal to a is the probability of x less than a minus probability of x less than a minus. So if suppose there is a you want to calculate the probability between a to b, if you want to calculate the probability between a to b, then it is fx of b minus fa minus लिख सकते हैं, fa minus लिख सकते हैं कहाँ पर, हाँ यहाँ पे लिख सकते हैं, ये fx of a minus लिख सकते हैं. The value of a and a minus will be different, but the value of a and a plus will be same. That is why it is continuous from the right. ओके अगर आप कैलकुलेट करना चाहते हो ए से बी के बीच में प्रोबेबिलिटी, तो इट इज द एफएक्स ऑफ बी माइनस एफएक्स ऑफ ए. अगर दोनों में डिसकंटिन्यूटी है तो आप ए प्रोबेबिलिटी ऑफ ए लिख रहे हो कि नहीं लिख रहे हो, ये इंपॉर्टेंट हो जाता है. जैसे कि अगर हम बोल रहे हैं कि इफ द एक्स इज कंटिन्यूअस एट ए एंड बी बोथ, देन एफएक्स ऑफ ए fx greater than a and less than equal to b is equal to fx of b minus fx of a. If suppose I include the probability of x equal to a here, if I include the fx of a here, then this probability of x equal to a has to be added. But because it is continuous at fx equal to a, so probability at x equal to a is 0. So ultimately probability x greater than equal to a less than equal to b is equal to fx of b minus fx of a. And agar we exclude x equal to b, then probability of x equal to b has to be subtracted. And if you subtract fx equal to b, then the probability of x equal to b is again 0. So there is no change in the relationship. So the formula will be same for all the cases, whether you put equal to sign or not, if the CDF is continuous at x equal to a and x equal to b. And the case number 2, if the CDF is having the discontinuity at x equal to a and x equal to b, then it becomes important that whether you are taking the x equal to a or not. Okay, if you are taking x equal to a, then you have to subtract or add the probability of x equal to a. यस अनंत, फिफ्थ पॉइंट में लिख सकते हैं बिकॉज वहां पे डिसकंटिन्यूटी था. Now the PDF is the differentiation of the CDF. PDF is the differentiation of the CDF. So the same example we will take and we will differentiate the same example. So if we differentiate this staircase form, then we will get this impulse which are having a height 1/4. As you can see that the example we are taking is because we were getting the staircase form CDF. So if the CDF is staircase form, that means the random variable is a discrete in nature. So if a discrete random variable is there, then the PDF is also in the form of impulse. So the PDF will be a pure impulse signal. It will be an impulse signal which is having the probability at x equal to a and x equal to x minus. Okay. Now, what is the property of PDF? The probability density function. The area under the probability density function is always equal to 1. The CDF is the differentiation. The CDF is nothing but the differentiation of x. The PDF is the differentiation of the CDF. So, because the CDF is non-decreasing function, so PDF will also be greater than 0. And if you want to suppose calculate the probability in a given range, then you have to integrate the PDF in a given range. And if I integrate from minus infinity to infinity, that means I am covering the total area under the PDF, so that is equal to 1. Yes, so total area is equal to 1. And if you want to calculate the probability in any range, then it is integration from x1 to x2. And if you want to calculate the fx of infinity, suppose, then upper limit is fixed. Suppose you want to calculate the CDF from the PDF. If you want to calculate the CDF from the PDF, so it is integration of PDF. So integration of PDF, but the limit is important. Integration of PDF, but the upper limit will always be same. Upper limit will be x. Guys, there is a scholarship test on 17th of January, that is 7:30 p.m. Or a scholarship test on 14th of January, and there are workshop on 17th of January. CDF is discrete in nature and PDF is continuous. Where the PDF is not continuous, PDF is not continuous, it is also discrete. This is a discrete type signal. No? So now we will discuss about the mean. Mean is nothing but the expected value of x equal to minus infinite to infinite x into f of x dx. For a discrete random variable, it is summation I equal to 1 to n xi probability of xi. So that means you have to multiply the value and its probability. Probability mass function discrete function ही तो है. Probability mass function यानी कि आप discrete form में तो लिख रहे हो. मास लिखोगे मतलब कि उसकी प्रोबेबिलिटी लिखोगे और उसको रिप्रेजेंट करोगे उसकी गिवन वैल्यूज में. Probability mass function. Okay, moment about origin is nothing but the x to the power n. X to the power n, expected value of x to the power n, that is integration from minus infinite to infinite x to the power n and the fx of x dx. This is for continuous. PDF, CDF, PMF are discrete. PDF for a discrete random variable, उसको छोड़ दो, उतना इग्नोर कर दो, उसको जरूरत नहीं है उसकी, है ना. आपको जरूरत नहीं पड़ेगा उसका. मैथ्स में जो प्रोबेबिलिटी मास फंक्शन पढ़ते हो उसी को ध्यान रखना, बाकी यहाँ पे आपको उसकी जरूरत नहीं पड़ेगी. जो प्रोबेबिलिटी मास फंक्शन से रिलेटेड जो क्वेश्चन आएगा वो मैथ्स से रिलेटेड आएगा. यहाँ पे अगर आएगा तो दैट विल बी ऑन द कंटिन्यूस, मेनली फॉर द कंटिन्यूस रैंडम वेरिएबल आपको देखने को मिलेगा. और डिस्क्रीट रैंडम वेरिएबल के लिए आप इम्पल्स के फॉर्म में पीडीएफ को लिख लोगे. तो मोमेंट अगर आपको कैलकुलेट करना है डिस्क्रीट के लिए तो आपको समेशन लगाना है इंटीग्रेशन की जगह x टू द पावर n एंड प्रोबेबिलिटी ऑफ x टू द पावर i. मतलब जिस भी रैंडम वेरिएबल का आप मीन निकालना चाहते हो उसकी प्रोबेबिलिटी और उसकी वैल्यू पता होना चाहिए, है ना. तो फिर आप उसको मल्टीप्लाई करके ऐड करते जाओ. अगर फर्स्ट ऑर्डर निकालोगे तो अगर x की पावर 1 रख दूंगा तो फर्स्ट ऑर्डर मोमेंट अबाउट ओरिजिन इज कॉल्ड मीन, मतलब आप x की पावर n था उसको 1 कर दिए तो यहाँ से आ गया minus infinite to infinite x to the power 1 fx of x dx, so that is mean. n equal to 2 रखोगे तो बहुत इंपॉर्टेंट रिलेशन मिलता है जो कि है मीन स्क्वायर वैल्यू, है ना. मीन स्क्वायर वैल्यू इज नथिंग बट द एवरेज पावर ऑफ द सिग्नल. सो कभी भी किसी भी सिग्नल का अगर हमको एवरेज पावर कैलकुलेट करना है तो वी कैलकुलेट इट्स मीन स्क्वायर वैल्यू. देन मोमेंट अबाउट मीन, अगर मोमेंट अबाउट मीन निकालना है तो x माइनस एक्स बार इज द मीन, तो मीन के अबाउट हम लोग मोमेंट निकालेंगे तो इंटीग्रेशन फ्रॉम माइनस इनफाइनाइट टू इनफाइनाइट x माइनस एक्स बार टू द पावर n fx of x dx, n is the order of the moment. मोमेंट पीवाईक्यू में नहीं आता है, मोमेंट में कोई पीवाईक्यू नहीं आया है, वो एक्चुअली मोमेंट का स्पेशल कंडीशन आपको आएगा, जैसे कि सेकंड ऑर्डर मोमेंट में बोला तो सेकंड ऑर्डर मोमेंट का क्या मतलब होता है, मीन स्क्वायर वैल्यू. तो आपको कभी कभी क्वेश्चन में मीन स्क्वायर वैल्यू लिखा मिल सकता है और यू कैन ऑल्सो गेट द सेकंड ऑर्डर मोमेंट. तो सेकंड ऑर्डर मोमेंट भी लिखा होगा तो आपको मीन स्क्वायर वैल्यू निकालना है. ठीक है, तो लाइकवाइज तो डिस्क्रीट रैंडम वेरिएबल के लिए समेशन i इक्वल टू 1 to n and xi minus x bar to the power n probability of xi आ जाएगा. So characteristic of the random variable n equal to 1, first order moment निकालेंगे mu1 is equal to expected value of x minus x bar to the power 1. Integration from minus infinite to infinite x minus x bar to the power n fx of dx. तो यहाँ पे मानना yes mean square value second order n इक्वल टू 2, यहाँ पे आपको मीन स्क्वायर वैल्यू मिल जाएगा. ये वेरिएंस के इक्वल होता है ना. वेरिएंस सेकंड ऑर्डर मीन, सेकंड ऑर्डर मोमेंट अबाउट मीन इज वेरिएंस, जो आपको इस तरीके से लिखना है. Okay, so now properties of mean. So properties of mean means expected value of c is equal to mean of constant is a constant itself, and mean value of ax plus b is ax bar plus b, and mean value of constant plus x is a constant outside आ जाएगा. expected value of x is x bar and expected value of x plus y is x bar plus y bar. ठीक है. Similarly आप variance का property देख सकते हो. Variance of constant is 0. Variance of cx is nothing but the c square into variance of x, and variance of ax plus b is a square and variance of x, and variance of x plus y is variance of x plus variance of y if x and y are independent. Variance of x plus y is not equal to variance of x plus variance of y if x and y are dependent. Now uniformly distributed random variable. Uniformly distributed random variable. A random variable is said to be uniformly distributed if the probability density function of x is defined as fx of x is equal to 1 upon b minus a to b, है ना. इसका यूनिफॉर्म का क्या मतलब है कि that should be flat, है ना. that should be flat. The probability density function should be flat in the range of a to b. In the range of a to b it should be flat. ठीक है. इसका मीन स्क्वायर वैल्यू और वेरिएंस लिख सकते हैं. तो by integrating this you can write its PDF. So from this PDF you can write the CDF, that is by integrating of this rectangular pulse. This rectangular pulse when we integrate we will get ramp. So that is the ramp. Now we have the negative rectangular pulse like this. So if this is the negative impulse, so we will get the flat curve here. So that is the overall CDF and PDF for the uniformly distributed random variable, right? What is the mean value of a uniformly distributed random variable? So for a uniformly distributed random variable, the mean value is a plus b by 2. So that is the mean value, a plus b by 2. And now mean square value of a uniformly distributed random variable. So mean square value for a uniformly distributed random variable is b square plus ab plus a square divided by 3. So that is your mean square value for uniformly distributed random variable. Yes, a plus b by 2, b square plus a by 2. And variance is b minus a whole square divided by 12. Yes, b minus a whole square divided by 12. A random variable is said to be Gaussian random variable if it is 1 upon root over 2 pi sigma x square e to the power minus of x minus x bar whole square divided by 2 sigma x square. Okay, now Gaussian random variable में आपके पास advantage है कि you don't need to calculate mean and variance because a random variable is Gaussian. If a random variable is Gaussian, then it is represented in the form of mean and its variance. So the first value is its mean and the second value is its variance. And if we plot it, it is a bell-shaped curve. So it is a bell-shaped curve 1 upon root over 2 pi sigma x square e to the power minus of x minus x bar whole square divided by 2 sigma x square. And here we will be having the bell-shaped curve which will have the maximum value, okay, 1 upon root over 2 pi sigma x square and at x bar, and otherwise it is 0.606. Okay, so it is always symmetrical about its mean. So Gaussian random variable is symmetrical about its mean value. Gaussian random variable is symmetrical about its mean value. Okay, now if suppose there is a Gaussian random variable which is having the mean x bar and the sigma x square is the variance which is 0 to 1, and it is symmetrical about variance mean because the mean is 0. Okay, the mean is 0, so it is symmetrical about its mean, and the value would be 1 upon root over 2 pi sigma x square into e to the power minus of x minus x bar whole square divided by 2 sigma x square, and sigma x is 1. So the plot will be 1 upon root over 2 pi e to the power minus x square by 2. So the plot which we have drawn is having this equation. The mathematical equation for this plot is 1 upon root 2 pi. So that is why we have got the maximum value at x equal to 0. When you put x equal to 0, it is e to the power 0, which is 1 upon root over 2 pi. So Gaussian random variable is always symmetrical about its mean. Always symmetrical about its mean. Now, how do you write the CDF of this? So the CDF is fx of x equal to minus infinite to x fx of lambda d lambda. Okay, and what is the CDF? If I want to write the CDF of a Gaussian random variable, it should be written in the form of x less than equal to x, जहाँ पे x जो है that is a Gaussian random variable. So we can write it as 1 minus q of x minus x bar divided by 2 sigma x. X minus x bar upon sigma x. Not 2. That is the CDF. for q function range is from x to infinity. Yes, q function, if you want to write the q function, then q function of x, suppose you want to write, then it is 1 upon root over 2 pi x to infinity e to the power minus y square by 2 dy. Okay, this is in the exponential, e to the power y square by 2. It is in the power of y. Okay, so q function is defined like this. The plot of the q function, if you want to see, then the plot of the q function is like this. At minus infinity, it is 1. At 0, it is 0.5. And at infinity, it is 0. So suppose there are some applications where we want to transfer the random variable from one type to another type. There we use this particular property, that is the transformation of random variable. So how do we transfer it? To transform this, we have a particular relation that is called your okay, so that is called the transformation of random variable. So depending upon the transformation type, whether it is a continuous type or discrete type, we have the transformation technique like monotonic transformation and the non-monotonic transformation. So for a continuous random variable, there is a monotonic transformation and non-monotonic transformation. For a discrete random variable also, there is a monotonic and non-monotonic transformation. So monotonic transformation means as you increase the value of x, the value of y is also increasing, and for each individual value of x there is a discrete value of y. So as you change the value of x, the value of y is changing. So x and y both we are getting. Okay, so the value of x and the value of y. So in this way we will get this one-to-one mapping. So for each value of x we have the value of y, and when we are increasing the value of x, the value of y is also increasing, hence it is monotonically increasing function. So when you increase the value of x and the value of y is decreasing, so when x1 is x is having some value x1, the value is y2, and when x is having the value x2, the value is y1. So the value of y1 is less than the y2, but the x is greater than the x1, hence this is called monotonically decreasing. So whenever you see this type of question, yes, they have asked about the CDF is a non-decreasing function, but it is not a CDF, Manasvi. This is a transformation. You have to see this plot. This plot is between y to x. The plot is in between y to x. This is not the plot of CDF versus x. So Fy of y is equal to, once you identify that which kind of transformation it is, then fx of x divided by dy by dx, that is your overall PDF of output. So PDF of output can be written as the PDF of input divided by dy by dx. And if there is a non-monotonic transformation, so for each value of x, you have to add the value of dy by dx after dividing it by the PDF. So the PDF you have to calculate for each individual value of x, like according to this expression, you have to calculate the PDF at x1, then calculate the dy by dx, and after calculating the dy by dx, put x equal to x1, plus calculate fx of x2 where it is having the same value, then dy by dx at x equal to x2, plus fx of x3, calculate dy by dx at x equal to x3. So all the different values of x for which you are getting the same value of y, you have to calculate the PDF and the differentiation at that particular point. So for a discrete random variable, again, if there is a one-to-one mapping, that means there is a monotonic transformation, whether it is increasing or decreasing. So if x1 is mapped into y1, x2 is mapped into y2, x3 is mapped into y3, xn is mapped into yn, then the probability of y1 is also same as probability of x1, probability of x2 is same as probability of y2, probability of y3 is same as probability of x3, and so on. So if it is a discrete random variable, then for a discrete random variable, the PDF is written in the form of impulse. So in the form of impulse, so calculate all the variety of impulse. Okay, calculate all the variety of impulse, y1, y2, y3, and so on. And then for uniform distribution, the transformation is non-monotonic. Let me see if I have a question. Okay, so for a discrete random variable, suppose this is the case. Let us say x is equal to -1, 1, and 3. And now if I want to calculate the y, when I put x equal to -1, it is 2. When I put x equal to 1, it is 2. When I put x equal to 3, it is 18. So it means there are two values, repeated values. So overall value of y is only 2 and 18. Na? Only two values of y. We have three inputs of x, but having only two values of y. So to write the PDF because it is discrete random variable, so the PDF would be in the form of impulse, that is summation I equal to 1 to 2, and then probability of yi and delta y minus yi. Or you can say that you have to calculate the probability of y equal to 2 and delta y minus 2, plus we have to calculate probability y equal to 18 delta y minus 18. So what is the probability of y equal to 2? So probability of y equal to 2 is y equal to 2 is coming because of x equal to -1 and x equal to -1 and probability of x equal to 1. So whenever the x is -1, y is 2. Whenever the x is 1, y is 2. So in this way, we have got these two probability are 1 by 2 and 1 by 4. Probability are 1 by 2 and 1 by 4. Probability of x equal to -1 is 1 by 2. Probability of x equal to 1 is 1 by 4. So 1 by 2 and 1 by 4 is 3 by 4. Okay. Okay. So now 3 by 4 is the probability of what? Y equal to 2. So probability of y equal to 2 is 3 by 4. Delta y minus 2 plus probability of y equal to 18. This y equal to 18 is coming because of x equal to 3. So probability of y equal to 18 is probability of x equal to 3. So what is the probability of x equal to 3? Probability of x equal to 3 is 1 by 4. So we will write 1 by 4 delta y minus 1 by y minus 18. Okay, now do you understand this? Okay, now we have this question. You can take one example that was asked in the previous gate. Let me show you that example. Suppose for continuous also I am telling Vikram, your doubt will be clear now. Suppose we have the suppose we have the PDF of x. Okay, that is fx of x ranging from -5 to 5. The height is 1 by 10. Okay, that is the PDF given. Okay, this is the PDF of x. PDF of random variable x. Now the transformation is given. Transformation is given as -2.5 to 2.5. The value is 1. Okay, this is the transformation, and this is the we want to find PDF of y. PDF of random variable y. Now, can you tell me the answer? See, here you can see that the x is transformed into y. So here you will see that when the x is in between -2.5 to 2.5, the transformation is y equal to 1. Okay, when x is in between -infinity to -2.5 and x is in between 2.5 to infinity. Okay, when this is the value of y is 0. So here you can see that the input random variable is continuous. This is continuous random variable, but it is transformed into discrete random variable because the output is having only two values, 0 and 1. So the probability density function the probability density function is y minus value of y is 0, so y minus 0 plus probability that y equal to 1 delta y minus 1. Okay, probability y equal to 0. Okay, probability that y equal to 0 will be probability that y equal to 0 is probability that x is minus infinity to minus 2.5 plus, because there are two reasons for which we are getting y equal to 0. So those two reasons we have to add the probability of them. Now tell me, what is the probability of these two? Yes. Yes, Vikram. Correct. So now the minus infinity, the probability you will calculate from here, minus infinity to minus 2.5. So area under the PDF will give you the probability. So this area and 2.5 to infinity, that means this area. So this area is minus 0.5, minus 2.5, minus 0.25, and this area is also 2.5, means area is actually plus. So this is 0.25, 0.25. So 0.25 plus 0.25 is added, which is 0.5. Now the probability of y equal to 1, probability of y equal to 1 means probability of y equal to 1, y is equal to 1 is coming because of x minus 2.5 to 2.5. So x is between minus 2.5 to 2.5 because of this. So probability that x is minus 2.5 to 2.5, which is 1 by 10. Okay. So 0.5. So the PDF fy of y, you will get probability of y equal to 0, probability of y equal to 0 is 0.5 delta y plus 0.5 delta y minus 1. Yes. So this will be our answer. Okay. So in this way you have to solve this question. Now tell me the answer of this. See, you are getting how it is possible to get C. Guys, the PDF is integration of CDF or differentiation, right? Differentiation. So when you differentiate it, so you should also take care that the area should be 1. Na? So answer is B. Area should be 1. So when you will differentiate it, the slope of this is 0.5. So the height should be 0.5. So that is the height 0.5. That is the height 0.5. the height jump is also 0.5 because the value of k is 1. The value of k will be 1 because at infinity the value is k and it should be 1. The CDF at infinity is 1. So the jump is 0.5. So this jump is 0.5. So area should be 1. So when you calculate the area, this is the 1 into 0.5, that is the width of the area of the rectangle, and area of impulse is 0.5. So PDF should have the area 1. Okay, the PDF should have the area 1. Yes. Now this is a basic question. Okay, yes, all of you know about this question. I think you also cover in the mathematics. Yes, Bashir. Now let's take this value, this question. What should be the answer of this question? Yes, so we want to calculate the probability that z greater than 2 given z greater than 1. It is probability that z greater than 2 intersection with z greater than 1 divided by probability that z greater than 1. So z greater than 2 and z greater than 1 is having the common part, which is probability z greater than 2 and z greater than 1. So we can write it as 1 minus probability that z less than equal to 2 and 1 minus probability that z less than equal to 1. So it is 1 minus 1 minus e to the power minus 2 divided by 1 minus e to the power minus 1. So it is e to the power minus 2 divided by e to the power minus 1. So it is e to the power minus 1. So 0.368 something. 0.368. Now answer this question. Yes, Vikram. See, this is the zero mean Gaussian PDF. So if it is zero mean Gaussian PDF, that means the PDF will be symmetrical about origin. Okay, so this is the PDF of what? X. This is the PDF of X. So if I ask you that what are the values of Y? So when the X is minus infinity to 0, when X is minus infinity to 0, the Y is equal to minus 1. So probability of Y equal to minus 1 is probability of X from minus infinity to 0. So what is the probability of minus infinity to 0? This region, because it is symmetrical about mean. So we know that the total area of the PDF is 1. So if it is symmetrical about origin, then it is in the left hand side, it has the probability 1 by 2. So the probability of Y equal to minus 1 is 1 by 2. So probability of Y equal to 1 is also 1 by 2. Hence the correct answer is option A. Joint random variable, no need. Now coming to the random process. Random process is nothing but the when we assign the real value time function in the random variable, when we do the mapping, we get the fixed real number to each sample point of the sample space. Sample space is having the different possible outcomes, and for each possible outcome we have a different output, right? And for each outcome of the experiment, if we assign the real number, then it is called random variable. And if we assign the real value time function, real value time function, okay, real value time function means at every instant of time the real value which is assigned to the sample point is also changing, then it is called the random process. So random process, we have to focus on the whenever we sample the random process, we get the random variable. So if it is given that we are taking the random process at time t is equal to t1 or t2 or t3, that means we are basically calculating the value of random variable. And we usually talk about the wide sense stationary random process. So wide sense stationary process are those wide sense stationary random process are those random process which is having the constant mean and the constant mean in autocorrelation function is a function of time delay. So a second order stationary random process is said to be Widej's stationary random process if the mean is constant, and when we calculate the autocorrelation comes function of time. And if it is discrete random process, then it is expected value of xn and xn plus k is equal to expected value of xn or xn plus k. So a discrete random process can be written in these two form. This is the representation. And ergodic random process, when you calculate the mean value and the time average value, then both will be same. Time average value of random process and mean value of random process both are same. And similarly for autocorrelation, if the time average autocorrelation and autocorrelation both are same, then that process is called ergodic random process. So for ergodic random process, we calculate the some properties about the autocorrelation, and this says that the autocorrelation is always having the highest value at tau equal to 0. This is important. Rest of the things which I have written was not that important. So first of all, you have to understand that how to calculate the random process. So to calculate the random process of any random process x, if you want to calculate the autocorrelation, then autocorrelation of a random process xt is expected value of x of t1 multiplied with x of t2. Okay, and the time delay between the two different instant is x. Time delay means t2 minus t1. Time delay means the difference between the two time instant. So if the xt is wide sense stationary, okay, then this autocorrelation when you calculate will become the function of time delay. That means the result will come as t2 minus t1, and that time delay is denoted by tau. So this is called Rx of tau. Okay, so if this process is satisfied, then we can write some properties about the autocorrelation, that Rx of 0 is greater or equal to than Rx of tau. Rx of tau is equal to Rx of minus tau, that is even symmetry. Rx of 0 is less than equal to expected value of x square t. That means at tau equal to 0, you will get the total power. And autocorrelation cannot have an arbitrary shape, and if the random process is periodic, then autocorrelation is also periodic with the same time period. And if the x of t is ergodic and there is no periodic component, then when you put tau tends to infinity, then it will give you the DC power, which is mean whole square. Now autocorrelation, after autocorrelation we have a cross correlation. So same thing, same definition. Rx by t1 comma t2 is expected value of x of t1 comma expected value of x of t1 into y of t2. The properties are xt and yt are orthogonal. Okay, for a wide sense stationary process, remember that for a wide sense stationary random process, the auto covariance is given by Cxx tau is equal to Rx tau minus x bar whole square. And wide sense stationary process, the cross covariance is defined as Cxy tau is equal to Rxy tau minus x bar y bar. So if it is a auto covariance, then obviously auto means the same process will be used. So this is Rx and x bar whole square, and as Cxy tau is equal to Rxy tau minus x bar y bar. So if Cxy tau equal to 0, then xt and yt are said to be uncorrelated. Okay, that xt and yt are uncorrelated. So power spectral density, the Sx of f is greater than 0, the property, and the total area under the power spectral density is 1. So if it is the minus infinity to infinity, Sx of f df is equal to 1 upon 2 pi minus infinity to infinite Sx of omega d omega, and Sx of f equal to Sx of minus f even symmetry, and Sx of f is always real. Then autocorrelation function and the power spectral density are Fourier transform pairs. So whenever you take the Fourier transform of autocorrelation, okay, whenever the Fourier transform of autocorrelation when you take, then you will get the power spectral density. Okay, so total power, if you want to calculate, is sum of AC power plus in autocorrelation function the maximum value at the origin. Maximum value at not at yes, origin only. Maximum value will be at tau equal to 0. So that means tau equal to 0 means origin. Okay. So how do you calculate the total power? How to calculate AC power and DC power separately? See, AC power, if you want to calculate, you have to calculate this part. Let me write this part and this part. This will be giving you the total AC power. Okay, because DC power means the DC frequency. The DC frequency means F equal to 0. So near to F equal to 0. Okay, Vikram? Yes, okay. DC power is not 0. DC power means you have to calculate at F equal to 0. We will see some questions so you will understand. So now if suppose you pass the any random process through the LTI system x of t, okay, then you will get the output y of t. So how do you calculate the relation between the output and the input power spectral density? So the relation between the output and input power spectral density is like this. So if you want to calculate the mean value of output, then it is mean value of input and h of 0. And if you want to calculate autocorrelation, this is convolution of Rx and h of minus tau. And if we want to calculate the Fourier transform, that means power spectral density, that is known as cross power spectral density. This is cross power spectral density. So cross power spectral density is Sxy, that is Sx of f into h complex conjugate of f, and Ry tau. Ry tau is h of tau, h of minus tau, and Rx of tau. So you have to convolve all the three, and Sy of f is equal to h of f mod square into Sx of f. So that is the relation between output and input power spectral density. Then if you suppose modulate the carrier using the random process, if you modulate the carrier using the random process, then the power spectral density of modulated signal will be, amplitude will get divided by 4, and this is Sx of f minus f naught plus Sx of f plus f naught. If the amplitude of sine and cosine is 1, then this amplitude is divided by 4. If the amplitude of sine and cosine is 2 cos omega naught t, then you don't need to divide it by 4. That will be then only shifting to the carrier frequency. Okay, if the cos is having amplitude 2, if the cos is having amplitude 2, then you don't have to divide the amplitude by 4. And if the cos or sine is having amplitude 1, then the power spectral density should be divided by 4. Cross power spectral density is not required. Okay, so there are few questions. Let's solve. Quickly answer these questions. There are few questions which will help you to understand what are the properties we have seen. Obviously, that revision marathon session is useful for those at least who have gone through all the concept once, because you cannot learn every concept through the marathon because we have limited time. So I will be finishing up in the digital communication also in the next hour. Mean 4, variance mean 5, variance 4, 5, 4. Okay, so mean we want to calculate at tau tends to infinite, limit tau tends to infinite rx tau. So when this is tau tends to infinity, it is coming as 25, and this is equal to mean whole square. So yes, mean is 5. Mean is 5. And what about the mean square value? Mean square value is at tau equal to 0, it is 29. So the variance is mean square value minus mean whole square. So 29 minus 25 equal to 4. Correct. Now answer this one. Anyone? Yes. So we have got the second order moment. The second order moment is expected value of x of 5 minus x of 2 whole square. So it can be written as expected value of x square 5 plus expected value of x square 2 minus 2 into expected value of x of 2 and x of 5. So this is nothing but the autocorrelation at 0, because this is mean square value and this is also mean square value, and Rx of 3. So Rx of 3, yes. So it is Rx of 0, so 2 into Rx of 0 minus 2 into Rx of 3. So when Rx of 0, when you put tau equal to 0, you will get A, and when you put 3, so you will get e to power minus 3 tau, 3 alpha, yes, minus 3 alpha. So 2a is common and 1 minus e to the power minus 3 alpha will come. So option D will come. Now try this question. Yes, Prabhat, you can prepare analog communication completely. So you are getting 0.5. See, here the random variable, we are having the t equal to 1. So at t equal to 1, if I substitute, this is cos 2 pi into 1 plus phi. So that means this x of 1 is 2 cos y. So now the random variable y equal to 0. So when we have y equal to 0, the random variable is having the value 2. And when the y equal to pi by 2, we have x of 1 equals okay, x equal to 1 equals pi by 2 means 0. Okay, so we are actually performing the transformation, you can say. So probability of x1 equal to 2 is probability of y equal to 0, which is 1 by 2. Okay, so answer is 1. Answer is 1. Mean value of xt. Mean value of xt 1, because at t equal to 1. So this is a discrete. So I equal to 1 to 2 probability and multiply with its value. So we have the values, that is 2, and it is having the probability 1 by 2, and this is 0. 0 is also having the probability 1 by 2. So it is 1. Okay, the probability of x1 equal to 0. Probability of y equal to pi by 2. So probability of y equal to pi by 2 means this is also 1 by 2, because y equal to pi by 2 is also having correct. Now try this question. No, it is not like that. Sorry, just wait a second. If we integrate autocorrelation, then we don't get mean value. It is correct, an incorrect statement. Okay. What is the answer of this question? So here you are getting yt equal to xt minus xt minus t naught. Okay, that is the output random process, and we want to calculate the autocorrelation of output. So Ry tau is expected value of yt and yt plus tau. See, expected value of x of t minus x of t minus t naught and x of t plus tau minus x of t plus tau minus t naught. When you multiply this x of t and x of t plus tau plus expected value of minus x of t minus t naught and x of t plus tau minus expected value of x of t minus t naught and x of t plus this is x of t and x of t and x of t minus t naught x of t t plus tau x of t. Okay, this is multiplied with this. This is multiplied with this. Now x of t, x of expected x of t plus tau minus t naught, and minus minus will become plus. Expected value of x of t minus t naught, x of t plus tau minus t naught. So 2 times of Rx of tau minus Rx of tau plus t naught minus of Rx of tau minus t naught. So answer is option B. 2 times Rx tau. Okay. Any doubt in this? Just tell me if you have any doubt. Okay, what I need to tell here. Now try this also. You will understand, Bashir. You have to calculate the autocorrelation of y. Okay, I am telling you the hint that you have to calculate the autocorrelation of y. Once you calculate the autocorrelation of y, you will get the result. T plus T naught and T minus, how I should be reverse, sir? See, Jaswant, they are even function. So if they are even function, so you write tau minus T naught or T minus that is same thing. Means if you reverse it also, then also there is same thing. But T plus tau you are getting there. You take minus sign common, you will get the same thing. So we have yt is equal to x 2t minus 1. Okay. So मैं बोला आपको कि you have to calculate the autocorrelation of y. Okay, so autocorrelation of y by the formula expected value of yt and yt plus tau. Expected value of x 2t minus 1 and x of 2t. T is replaced by t plus tau, so 2t plus 2 tau minus 1 will come. Whenever there are same process, the time delay between them, so this will be considered as t2, this will be considered as t1. So the time delay is t2 minus t1. So the t2 minus t1 will be 2 tau. So this will become Rx of 2 tau. So autocorrelation of Ry tau is Rx 2 tau. Now taking Fourier transform. Okay, so taking Fourier transform, you will get Sy of f is equal to 1 upon a Sx of f by a by scaling property. By scaling property of Fourier transform. So 1 by 2 Sx of f by 2. Now can you answer this question? Yes, so what is the answer of this question? See, there is a triangular function. So if you will have a triangular signal, okay, this is a triangular signal, suppose we are drawing this triangular signal. This is the standard triangular signal only, na? So, and when f equal to 0, we will put, so f equal to 0 means you will get 3 into 10 to the power minus 3, because f equal to 0 means 3000 into 10 to the power minus 6. है ना? And when we put f equal to 1000, okay, this is in kilohertz, so f is equal to 1000, so 3000 minus 1000 is 2000, okay, and when we put 2000, so it is 2000 into 10 to the power minus 6, so 2 into 10 to the power minus 6, so you will get 1 and you will get 2, so here it is 1 into 10 to the power minus 3. So the same thing you will get over here, minus 1 minus 2 minus 3 plus 3, and now you are modulating the carrier which is having the frequency 8 kilohertz. So now you are modulating the carrier having the frequency 8 kilohertz. So that means your power spectral density will shift to 8 kilohertz as we discussed, and amplitude will get divided by 4 because the carrier amplitude is 1. So 3 into 10 to the power minus 3 will be divided by 4. 2 into 10 to the power minus 3 will be divided by 4. 1 into 10 to the power minus 3 divided by 4. And the peak value will shift to the carrier frequency, which is 8. So now it is 8 plus 3, 11. 8 minus 3, 5. 8 minus 1, 7. 8 plus 1, 9. And this is 6 and this is 10. Yes. So this will be getting, and we are passing it through the band pass filter having the, we are going to pass it through the band pass filter, which is between 7 to 9, because the bandwidth is 2 kilohertz and the center frequency is 8. So bandwidth is 2 kilohertz means it should be ranging from 7 to 9. Similarly, in the negative side, so minus 8, minus 9, minus 7. Divide by 4 because the amplitude, whenever you perform the modulation in the power spectral density will get divided by 4. Okay, power spectrum density will get divided by 4. That is what we had already written in the properties. Okay, I told you that whenever you modulate the carrier with the random process, then the amplitude will get divided by 4, and when the amplitude of the cos is 2, then 2 square is 4, so it will not get divided. So that means, I will tell you again. Okay, so suppose there is a random process xt, okay, and here you have AC cos omega ct, then your power spectral density is AC square by 4 Sx of f minus fc and Sx of f plus fc. So here, if the AC is 1, that is 1 by 4. If AC is 2, so 2 square by 4, that means 1. Okay, so what will be the output of this filter? So output of this filter will be having this kind of shape. Okay, this is the output power spectral density. This is your filter. Okay, and here the amplitude is 2 into 10 to the power minus 3 divided by 4. And the peak value is 3 into 10 to the power minus 3 divided by 4. So total area under power spectral density. Total area under power spectral density gives you the power. So calculate the area. So this is 7, this is 9. So area is 2 into 10 to the power 3 because we are calculating in kilohertz. So 2 into 10 to the power 3, and height is 2 into 10 to the power minus 3 divided by 4. Okay, plus the area of this triangle. So 1 by 2 into base is 2 into 10 to the power 3 and height is 1 into 10 to the power minus 3 divided by 4. That is the area of the right hand side. Now multiply it by 2. So when you multiply it by 2, you will get the power, okay, the average power you will be having 2 into 2 into 4, 4 and 4 get cancelled, 10 to the power 3 will get cancelled, 1 plus. 2 and 2 will get cancelled, 10 to the power 3 will cancel, 1 by 4 into 2. So it is 10 upon 4, which is 2.5. So 2.5 will be the right answer for this question. 2.5. Integration of autocorrelation. Why you want to calculate integration? So we can find DC power by integrating the autocorrelation. No, by integrating the autocorrelation you will not find. And this question you cannot take. Okay, can you answer this question? Can you answer this question? We can find power spectral density. Power spectral density you can find by taking inverse Fourier transform. Chintu, Praveen, from the digital communication, you can expect at least digital communication means accept random variable and random process. If I say, then you can expect 3 questions. 3 questions from the digital communication. And remaining 3 questions from the analog and the random variable and random process. Analog communication and random process will take around 2 or 3, and digital communication will surely have 3 questions minimum. It can go maximum up to 5. Who can solve this question? What is the idea behind this? We have discussed today itself. If you want to calculate the transmission efficiency, then it is k square into Sx upon 1 plus k square into Sx. What is Sx? Is the signal power. Now I have given you a hint. Now tell me what is the answer. Signal power. How do you calculate the signal power? Yes, signal power, average power. We calculate only average power in communication. We don't calculate the any other power like power spectral density not required. How do you calculate signal power, guys? Signal power means mean square value. Signal power means mean square value. And how do you calculate the mean square value of uniformly distributed? Because your signal is xt and xt is uniformly distributed. So b square plus ab plus a square divided by 3. B is plus 2. So plus 2 whole square plus minus 2 into 2 plus minus 2 whole square divided by 3. So this is 4. This is 4 will get cancelled. We will have 4 by 3. So K is 0.2. This is the value of Ka. So 0.2 whole square multiplied with 4 by 3 divided by 1 plus 0.2 whole square multiplied with 4 by 3. So answer will be 5.06%. Yes, 5.06%. Okay, now answer this question. 6.25, yes, because average sideband power, the average sideband power is nothing but the PCMA square by 2. The carrier power is 10 square divided by 2 into MA. MA is 0.5 square divided by 2. So we are having the 0.25 into 100. So 25 divided by 4 is 6.25. So 25 by 4 we are having. Okay. So now the same question related to this. 6.25 is the answer. That's the mistake that usually the student does. Average means doesn't mean that you have to take all half of that value. Okay. Average doesn't mean we calculate average value only. The average value itself is PCMA square by 2. So don't take average of upper sideband, lower sideband and divide it by 2. Then you will get the wrong answer, 3.125. The same question linked with this. So here you have to calculate the ratio of average sideband power to the mean noise power. So noise power means noise power spectral density is given. So calculate the power of any one sideband and multiply it by 4. Okay, calculate the power of one sideband, one of this graph. So calculate the power of this. So 1 by 2, base is B, height is n naught by 2. So how much it is? N naught B upon 4. That is the sideband power of only one section. We have total 4 spectrum symmetrical. So that means the total noise power. Total noise power is 4 multiplied with n naught B by 4. So 4 and 4 will get cancelled. We will have n naught into B. So signal power is 25 by 4, 25 by 4, and the noise power is n naught into B. So option B will be the right answer. Amplitude is not one where you have seen amplitude. See, Manasvi, here the power of your noise is separately given. Noise power is separately given and the signal power is separately given. Signal power we calculated using the amplitude modulation. Noise power we calculated from the noise power spectral density. Both we calculated separately and then we have to take the ratio. Okay, so to take this ratio, we have calculated the noise power here, which is n naught into B, signal power in the previous part, which was 25 by 4. Take the ratio, get the 25 upon 4 n naught B. Guys, so this is it from my side today. Digital communication we will be taking in the separate session. Okay, digital communication in separate session, which will be in the next few days after you have 3 or more marathon session. Then digital communication we will take separately because it will again take around 3 hours. So we will take that separately so that you will get benefited. Okay, because if I will try to cover it now, then it will be a very short duration because I cannot extend more than 30 minutes now. So it will be like going through the formula only. So we will take this digital communication separately in the upcoming session. After the 3-4 days, you are having a 3 to 4 marathons lineup. After that, we will take them. There will be a digital communication and information theory both. So information theory and the digital communication both I will cover in the same time. And guys, here we have a QR code, so you can attend the quiz. Okay, join the quiz now. Attend the quiz right now. That whatever you have studied in this marathon, you will be getting the questions related to the analog communication, random and digital. So leave the digital part, solve amplitude modulation, angle modulation, receivers, random process, random variable. Okay. Information, tomorrow is also there is a marathon. Thank you, Manasvi. So we will be taking the digital communication separately in the next session, which will be around after 3 to 4 days. And I hope that this session is useful, because I have taken complete time to revise all the concepts through the questions also and theoretical part also. That's why it took time. If I just go through some formula and questions, then I would have finished the syllabus, complete syllabus entirely in these 5 hours. But because I went through most of the concepts, that's why it took time. So this is my Telegram group. You can join if you are interested. Thank you, and we will be taking the digital communication in the separate marathon series. Thank you so much. Good night. Take care, and all the very best for your exam. Thank you.